Welcome, welcome again. My name is Lee Barney. I am one of the workshop chairs, and we want to welcome everybody who's here and online. We have a bunch of research papers that we've got submitted, and we're excited to have everybody present those. We've got some other things going on as well that I think you'll find really interesting. We did receive 11 submissions altogether, which we were very grateful for. And you can find the schedule online. This is our program committee, and we would like to thank everybody who has participated in the creation of this conference. We really are very grateful. The steering committee is also these individuals, and we're very grateful for them. We have several sponsors, and that has been very useful in helping us put this together and to get people so that they could participate. One of them is the Erlang Ecosystem Foundation, and if you're doing research in this area and are not a member, I would strongly encourage you to be a member. And specifically, I would suggest you become a paying member. And it's not hugely expensive, but it is very, very helpful to the Erlang Ecosystem Foundation. The EEF is one of the organizations that spends its time making sure that the community and the platform are available and secure. And Jonathan has done a great deal of work there. So please, if you are not already a member, please join. And if you can, please be a paying member. So we have 3 minutes before our scheduled first presenter, which will be our keynote. So, yeah, absolutely.
How did you find the rejected papers? Were there AI slop papers, or were they?
No, no. We didn't notice any huge AI slop stuff coming through.
That's reassuring. Good.
Yeah, they were generally really good, just not oftentimes quite all the way done, would be a good way to put it. So, all right. So, come on up. Let me disconnect.
Actually, that's
Yep, sorry.
all right.
Okay. So Colin S. Gordon is our keynote speaker today. He's an assistant professor of computer science at Drexel University. His research focuses on programming languages and formal methods, particularly type systems, verification, concurrency capabilities, and effect systems. And he's going to speak to us today about actor capabilities for controlled actor interactions. Thank you, Colin. Please welcome Colin.
All right. Thank you. As the talk title suggests, you'll be here. So we're going to talk about basically actors, capabilities, and applications of these ideas to Elixir. So this is an outgrowth of some stuff that I presented at Golaga's Festschrift, working out these ideas on a core calculus. But of course, we know not everything that works for a tiny core calculus works for real things. So it's also more fun to analyze real programs. And ideally, not only for me to analyze real programs, but to build something other people can use to analyze their programs without needing to be me. So let's talk about evolving these ideas, both what the ideas are, but also evolving them to deal with Elixir. So we're going to talk about some things that work. We're going to talk about some things that are works in progress. Some of the challenges that are really cool problems to solve when you try to tackle real things instead of core calculi, as well as sort of the subtext of that designing for an existing language is different than designing for a new language that you made from scratch, right? Which is something that the Erlang community has a lot of experience with, building the languages first, and then retrofitting typing approaches, for example. So the original version of these ideas was cast for a core calculus that has a lot in common with typed akka. So the calculus was close to what's in Golaga's dissertation. But it was structured in a way that Beam languages like Erlang and Elixir are not. So in akka, generally you define an actor basically by this behavior, which is essentially a message handler and what it's supposed to do. So a behavior message base is supposed to be a message handler that's ready to handle anything of type message base, including all of its subtypes. And then after it does its important work, here, logging, it's supposed to then return the handler to use for the next message. And so we do often end up with cases like this one where we have to recursively define behaviors. There are some shorthands that are a little more convenient in actual akka, but we can explicitly define things recursively so that this behavior returns itself. And so the next message will be handled exactly the same as the first message, and so on, and so on, and so on. And we can take that, and we can sort of carry that over to Elixir and get something that superficially looks a little similar. And this, of course, will do the same thing. So if this loop becomes the body of a new process that we spawn, this will, again, wait over and over for a particular message type. Let's assume I've defined that is message guard somewhere. It will log them, and then it will do this again. But the way it accomplishes this is very different, and it turns out a little more subtle and trickier to reason about. Because in the akka case, the message handling is passive. The framework hands off messages to a callback one at a time. Here, the message handling is active. This receive block is an active piece of things in the control flow of the program, and it will stop execution and wait until there's a message that matches this guard. Then it will continue on, but instead of returning a handler that the language or framework invokes on its own later, this is direct control flow. So there's a little less structure in the sequencing of message handling here, which is reflective of what larger scale real programs in the actor style tends to look like. Now, of course, once we start talking about slightly larger programs, even just very slightly larger programs, we get into cases of things like phased execution. So this is a slightly, just barely more complicated actor. This one has effectively two behaviors. So if we start the process running this initial behavior, it will sit there and wait until it gets an initialization message, log it, and then switch gears. It will switch over to this steady behavior here, where we go up here and we start waiting for a bunch of act and no-op messages over and over and over. So this actor, if we start with the initial behavior, expects one init and then a whole bunch of act and no-op messages. But of course, somebody might send those messages out of order, right? So in general, weird things can happen if messages don't show up in the order they are expected, right? So in some cases, you end up crashing. But the more general case is if you look at almost any beginner material on learning Elixir or Erlang, they will generally nudge you pretty hard towards you should almost always have a catch-all case for unexpected messages, just in case. And the reason for this is if we go into that steady behavior, we're expecting a bunch of acts and no-ops. If we get those, we process them. But if an init shows up late, it will just sit in the mailbox. This receive will skip over it without that catch-all case. And then those can pile up if they keep showing up, and we might overflow the mailbox. On the initial behavior side, if there's already an act or a no-op in there before the init shows up, this is kind of OK. It will wait till the init shows up and then switch behaviors, and then it will eventually handle those things. But now we're handling them in a different order than the sender might have expected. So for some messages, this doesn't matter. For other messages that maybe have external effects on the world, the order in which we process them does matter. So there might be some expectations on the sender side that if we send A and then B, they will be processed on the receiving side in that same order. The other thing is, if we throw this catch-all case in here, it's also kind of mixing together two different concerns, right? Because it's not clear if these things are showing up out of order. Are they showing up out of order because this is the nature of distributed systems and things have interesting ways of showing up in unexpected orderings? Or is it because we actually are just in a large program and we made a mistake somewhere, right? Maybe we just flat out wrote the sends in the wrong order without thinking about it. And it's hard to tease these two things apart because sometimes, at least for testing, we might want to throw so we catch the error right away versus, for example, just sticking it in a log. And realistically, once you get an enormous log, how often are we going to look back and actually find these subtle, funny messages showing up out of order? So we'd like to have some way of teasing these concerns apart. Now, of course, this is an old concern, right? This idea of reasoning about what order messages show up in a distributed system is a really classic problem. Lots of people have looked at it, from session types to mailbox types to countless other approaches. But of course, every person who comes and looks at this problem or any other problem comes with different background, different experience, different priors, and they sort of hone in on different pieces of what's the right place to interpose to try to control this. So my brain, addled by more years than I can keep track of building type capability systems, of course, looks at this and says, aha, it's a type capability problem. So that's the direction we're going to go. But I am going to explain why this is not just my priors and something I can hammer away at to make it work, but also actually the right fit for the problem, which is the important thing that is easy to overlook. So when I look at this, the problem I see is, hey, the senders can send messages to an actor in whatever order they please. If they have an actor F in Akka, if they have a PID in Elixir or Erlang, they can send whatever messages they want in whatever order, and there's no checking that this is actually the order we are intending to get them on the other side. Sometimes we don't care, and we can always express lack of care about ordering, but sometimes we do care, and we'd like to be able to express that too. So we're going to build a system that lets us restrict how senders use an actor ref or a PID, in this case, to send stuff to another actor or another process. And once we've done that, we have a strong foothold to build additional machinery that we layer on top of, complementary to that, to reason about what order the recipient will actually try to handle the messages to make sure that's actually consistent. And we're going to use slightly different but complementary approaches to doing this, which avoids this problem of trying to use one super powerful tool for everything, which I think tends to lead to very, very complicated specifications. So I don't know how many people here in the room or following online are people who are deeply in the Erlang or Elixir community or other Beam languages or actor systems, and how many people are just sort of sidecarring this on ICFP. So I'll pause to point out that it's true that the tagline for actors, one of the big taglines is they're actors, right? Especially with Erlang OTP. Let it fail, right? Let it fail and restart, right? What's the big deal? And the big deal is, of course, we do want robust support for tolerating failures when they are unexpected, but that doesn't mean we just want, it's okay to just add extra errors. So if we can pull some of these errors out, that are avoidable, let's do it. Because if we don't, if we restart too often, we can cause other things to fail. Or drag down performance, right? I said before that if we have unhandled messages piling up in a mailbox, actually the receive scans from the start of the message mailbox every single time, so it gets slower and slower and slower. Or if you're crashing all the time, you're losing data. This might be client data. Should the client retry if they haven't heard an acknowledgement? They should. If you don't own the client's code, will they? Maybe, maybe not. So we'd like to have some way of avoiding these things, but more important, we want the option to use the tools to avoid these things, not necessarily being forced to use these tools to avoid these things. And so the key concept that we're going to employ here is this thing called a capability, right? Which a lot of people have probably heard of, and it's a really old idea, goes way back to the 60s. And there are some subtleties, some of which we'll touch on later, others of which I'll gloss over for time. But the core concept is beautifully simple. The idea is if you have a program and you want to reason about, does my program do X? Maybe it's send stuff over the network, touch this file, things of that. Whatever X is that you care about, you set it up so that in order to do that operation, the program has to present this magic value called a capability to the operation. It has to be some magic value that it can't forge. So clearly this doesn't work in C. It can't be an integer, right? You need some kind of type safety, but most of our languages are type safe, modular reflection. And once you've done this, anytime you can convince yourself, hey, this capability for that file or this capability for the network does not enter that part of the program, you get to conclude, hey, that part of the program doesn't do the operation because it either can't invoke it at all or the operation will just say, hey, sorry, you didn't give me the capability, so no. Right? So it doesn't mean it doesn't try, but it means it doesn't actually do it. Right? And so this is a classic idea, and it turns out it's a beautiful fit for actor-based programming languages because it turns out we're already using capabilities when we're programming with actors, right? A PID or an actor ref is a dynamic capability of a sort because you can't send a message to an actor you can't name, right? If you want to write a message send, you have to put something in the destination part of the operation. And if you don't have a thing to put there, you're clearly not sending the message, right? Or you could put nil or something, but of course that, again, it won't work. So this is already a kind of capability. And in certain typed settings, like Akka's typed variant, as well as some other frameworks, this is also a statically checked capability and what I'm calling a reference capability. Right? So it's statically checked because if you have an actor ref T in Akka, you can only send things of type T. It might be that the actor is willing to handle other stuff beyond just stuff of type T, but with that capability, with that token, you can only send things of that one type, right? Or its subtypes. I'm calling it a reference capability because it has this property that's shared with reference capabilities in the literature, where you can have aliases that have different permissions. So you can have an actor ref T and an actor ref U for two totally unrelated types that both point to the same actor. But if you want to send a T, you need to use the actor ref T. If you want to send a U, you have to use the actor ref U, which raises the question, how do you get actor refs for different types if initially the actor is going to handle some super type of all common messages? And the answer is subtyping. So in Akka and a lot of other systems, these actor references or these handles are contravariant. So if an actor summons its own self-reference by saying, give me a reference to itself, if this is done inside a message handler that's accepting things of type, message-based type, well, you can coerce this to an actor ref that only lets you send a select subtype. Because maybe we're sending off a handle for a return message to a process that we don't want to hear anything much from except for one particular message, right? And this actually happens quite a lot in Akka programs. So this is something that people are already doing. It's already a natural fit for the programming model. So let's just embellish it a little bit more. Now, the reason it's productive to look at things this way is because one of the things capabilities, including these that are already existing, are really good at is establishing very strong global guarantees about program behavior with extremely localized checks, right? Not just modular checks, but where the specifications, the descriptions of behavior are extremely local. So for things like typed akka, we get this nice three-way agreement where we establish this invariant that I'll call behavior capability consistency, right? The idea that at any time, the set of outstanding references to an actor will only allow you to send things that the actor is ready to receive, right? And clearly this is true when we start an actor. We create a new actor from a message handler, a behavior T, that will handle messages of type T. And the first reference we get back is an actor ref that lets us send actor ref, it lets us send T. So we have one handle that lets us send T. We have an actor that will receive T. Everything's good. But of course, both sides of this relationship can evolve independently, right? We can derive new capabilities, new actor references from old. We can change the behavior of the actor over time. And so we can have two pieces, right? So on the sender side, we want to enforce this guarantee or this restriction that I'm calling capability preservation. If you've read some capability literature, you might have heard this term capability monotonicity floating around. This is that, but when we're talking about typing the up and down direction, sometimes gets people mixed up. The idea is, if you have an actor ref T, there's nothing you can do to that handle itself to let you amplify what you can send. If you start with an actor ref T, all you can send are things of type T. As we saw on the last slide, you can get weaker actor references that let you send less than you started with, but you can't get a stronger one that lets you send more, right? Which means when we derive more actor references from that original, they're still going to have the same upper bound on what they're sending to that actor. And on the receive side, turns out, at least in akka and some other calculi, this is invariant because the message handler, right, after we handle a message of type T, we have to return another message handler that's ready for messages of type T. So we're sort of committed forever to handling messages of type T. Right? So these are the key ideas we're going to be exploring. So let's take this and let's explore it for Elixir, and let's adapt it for message types that change over time. So if we walk over to Elixir, it's easy to say, well, this actor ref T idea becomes PID of T. And of course, those of you who have written a lot of type specs are probably thinking, but PID doesn't have any arguments. And that's true. And we're kind of reinterpreting or redefining, right? So we could kind of say, well, PID 0 is basically PID dynamic, right? It's a PID that lets you send anything you want with no guarantees of type safety on the other end. That's basically what it does. So we're finding a way to sort of fit the system that exists today into what we're doing. So this is sort of the guiding principle, is to build a system where the existing way things are done is just a special case of what we're trying to do. And so we have this dynamic type here, and so this is a good time to mention that Elixir has an existing type system that is part of the language. You get type errors from Elixir right now as of a couple months ago. 120 came out in June, I think. Based on some nice work from a few folks, including the creator of Elixir, which briefly combines set theoretic types. So you have literal set theoretic union intersection negation, plus semantic subtyping, as has been used in quite a number of contexts, along with some interesting solutions for parts of Elixir that are kind of unique and really cool. And we won't spend a lot of time on them, but these papers on this sort of hybrid fused map record struct thing are very cool. At the moment, all of the types are inferred. You can't actually write type annotations in Elixir right now, although the plan is to do that in the future. So you're going to see things that look like type annotations in my code, but they're just for demonstration and expository purposes. You can't actually write them today. So the next step is, OK, so we've kind of built out enough infrastructure by saying, let's stick a type in the PID. that we can talk about an upper bound on message types, but let's push that a step further to talk about the sequence of message types we expect to receive. So let's switch from having a PID that talks about one type that's an upper bound to a PID that talks about sequences of types of messages we expect to send. So this lets us say things like, well, we can have a PID act that lets us send exactly one act. So this colon act thing here, this is an atom in Elixir. It's very similar to a symbol in other languages. I'm going to use those for clarity in a lot of the examples here. We can have a PID nop star, right? You can send as many no-ops as you want, right? 0 or more. And in general, I'm going to draw a lot of examples from the regular languages. In principle, we're using a bunch of operations. The only language class I know works with all of them is regular languages. But maybe something more flexible works too. We'll see in the future. So when we send messages, we want to then check if we're actually following the design intent expressed by these types, right? So writing these types down says what we expect to do with them, but we want to check conformance to that. So when we send a message via a PID-L, we want to check two things. First, we want to check, are we allowed to send this as the first thing in some sequence we're supposed to send, right? So we can't send a nop through an act, but we can send a nop through a PID for nop star. We can send an act through a PID act, but we can't send an act through a PID nop star. And once we've done that, we've now maybe committed ourselves to certain subsets of the sequences we're allowed to send. And so we need to update the type. We need to keep track of the fact that we've now taken a step through one of these sequences, and now the next thing we send needs to be a continuation of the sequence that we started to send. So this leads to a type rule that looks something like this, where the idea is basically we're going to type whatever message expression we're sending. It's got a type. We have an output type context because, like I said, we're going to change the types of PIDs as we work through the program. There's an effect that we'll come back to later. The main thing is that the first check we do, can we send a tau first, we can do with this residual, derivative. So this derivative of L by tau is basically computing for the sequences that this language L describes, what are the valid continuations after we start with a tau that would still give us an overall result in this original language. And so if that set is non-empty, that means that there is a valid way to continue this sequence. And we update the PID to say, basically what we're allowed to send next. And so if we pull together a few examples, if we start with a PID that lets us send any number of nops, then one act, then any number of nops. If we send a no-op, that's fine, right? Clearly, we can send a no-op first. And after we've sent one no-op, well, we're allowed to send any number of no-ops, so the type doesn't actually change, right? On the other hand, if we start with the same type and then we send an act instead, we have to look a little further visually to see, yes, we're allowed to send an act first, but the language theory is the same. And then afterwards, we've now, we've executed sort of that much of the allowable sequences, so all we're left with after sending an act is more no-ops, which ensures that we're only sending no-ops after our one act. So this is cool. So now we can express the intended message sequences that we're going to send, and we can check that we're sticking with it. Yeah. Sorry. Gamma prime is the updated thing, right? So executing this expression might itself contain nested sends, which then update other PID types. Yeah, so this is a subtle detail. This is a slightly simplified rule. The real rule is a little more complicated because what we really want to do is we do want to deal with the reduction of P to something that we care about. And so if P comes from, say, a function call, clearly, yes, we need to keep track of whatever's happening, or if it contains a send, we need to do that. This rule on the screen only handles like variables and variable.field kind of accesses. So this is a special case. All right. So with the generalization that, as Ben has pointed out, I'm not showing you, this sounds really good, but of course there's a catch, right? Which is that if we're not careful, this actually becomes totally useless checks. In most type systems, if you have an expression on the right-hand side of an assignment and you assign to a fresh variable, the type of the new variable is the type of the thing on the right. We can't do that. So if we try to do that, and we do that naively, we can start with the same PID that we had on the last slide. We can copy it into a variable x, and if we naively copy that type there, what we get is x and y with the same type, and then we can use the rule on the last slide to send through x, one act, and we update its type like we did on the previous slide. And then we can use y to send another act, which seems wrong, because we started with permission to send one act, and now we've somehow sent two. So clearly we made a mistake, and that mistake was just blindly copying that type of x to the type of y. So this is not a totally new problem. There are a lot of capability systems where we have to deal with this problem of when we copy a value that is associated with certain permissions, sometimes we want to reason about, well, certain permissions go with that copy of the value, and certain permissions go with the other copy of the value. Some stay with the original, some go with the new copy. And since we want to be able to do this segmentation on formal languages, we need to go to the exercises section, the footnote of the exercises section in our undergrad theory of computation textbook, although this has been used heavily in interleaving semantics for concurrency for many years, and look at this shuffle operation, right? And so this shuffle operation is this idea that you can take two languages and you shuffle them together by taking a string from L1 and a string from L2 and shuffling them together like a deck of cards. It doesn't have to be a good shuffle. This counts. Splitting the deck counts. Any kind of awkward thing that you might do when you're learning to shuffle cards, it counts as a shuffle. It's legit as long as you don't reorder things from either side. So for example, if we want to say, well, I have an act and I want to shuffle it into a whole bunch of no-ops, well, we get this now familiar example of one act before and after any number of no-ops. And we can take this and we can use this to hook into this existing notion of splitting capabilities from prior reference capability work. So the idea there is that there's a separate judgment that tells us when we're copying a value, how are we going to divide the permissions of that original value between the updated original type and the copy. And so this rule, most of the rules basically just sort of recursively go down into different subtypes, and they all bottom out at this rule. So this rule says if you have a PID that lets you send sequences according to some language L, you can pick any new language you want for the updated original and the type of the new value, as long as when you shuffle them back together, you don't have more than you started with. So this is where we're enforcing that capability preservation or capability monotonicity. We're not letting us amplify permissions when we copy values around. And this is a pretty flexible notion. So if we take that PID type from the previous slide, if we can split that in a number of different ways. We can pull out just the act and then one no-op. We've forgotten permissions to do all sorts of things in that process. We could pull just the act out from all of the no-ops. We could pull out a whole bunch of no-ops apart from a copy of the original type. And all of these work because none of them let us do anything with the resulting two values that we couldn't have done with the original one. So at this point, we have this pretty rich notion of what a PID could be and how we can use it, but we're still in this land of designing for a language that already exists, right? Elixir has an existing type system. So we should pause and ask, does this still fit? Like, do we run into weird problems when we try to add this to Elixir's type system? And the short answer here is no. So PID is going to be contravariant, just like it is in, for example, Akka's typed API. It's always sound to forget you're allowed to do some things that you're allowed to do. right? That will never let you do extra stuff. And if we really wanted to, we could sort of justify this by appeal to splitting. But the short version is, if we look at what happens with union and intersection types, it's pretty easy to pass union and intersection of PID types into a single PID type with different operations applied to the languages. So if we have the intersection of two PID types, we have something that's allowed to be used as a PID L1 and it's allowed to be used as a PID L2. Well, that means that effectively you can pick if you want to follow L1 or L2, which means we have effectively a PID for the union of the two languages. And if we have a union type, we don't know if this is a PID L1 or a PID L2, it's one or the other. Well, the only things that it's safe to send to it then are things you could send to either one, i.e. send things to the intersection. Right? So pausing and taking stock, we have this PID-L capability type idea that lets us express restrictions on senders. It's highly localized checking. It seems to fit with Elixir's existing type system. And we're going to build more stuff, but I want to point out that it's useful even if we stop here. So even if we stop here, if we go back to that example at the beginning where I was raising questions about, do we have this catch-all because we messed up and sent stuff the wrong order ourselves, or do we have this because we actually need to be tolerant of out-of-order message deliveries in a distributed system? This gives us a handle on that. If all of the incoming PIDs to a given actor are using these protocols, all of those PIDs originated in this actor's code. So that means when we're tracking down the root cause of the bug, if there is one, is now not somewhere in the program, it's in this actor's code. So even though the semantic property we're getting is kind of on the weaker side for work in this space, it's, other actors send messages in the orders they were told they can send them, we're still getting a good software engineering benefit of localizing where to look for problems. But once we have all of this control over the sender side, we can turn our attention to the receive side, to an actor and its handling of messages. So recall the early incarnation of these ideas targeted a simple core calculus where there was an explicit behavior type for message handlers, and the messages are dispatched by the framework. So there's a very systematic fixed granularity at which messages are delivered and times at which messages may be delivered. And the fact that each handler explicitly returns the next handler to use, this tells us a lot about basically when we transition from handling one message to handling to the next. It's a very rigid framework. Still very powerful, right? People build lots of stuff in Akka, but it's much more rigid than the Beam languages. Right? So with all these restrictions, we actually just need like this one clean type rule to type behaviors, and we get all sorts of nice guarantees. But Elixir's a lot more flexible. So Elixir has, again, this explicit blocking receive, right? Processes can call this receive anytime they want. They can receive, and in one of the branches of the receive again, right? The receive is selective. So it's possible to intentionally receive messages in a different order than they were sent, with some limits that we'll talk about. The other thing is that the dispatch to the next message handling is just regular control flow. It's not sort of this implicit fixed granularity thing, so we need to be able to handle all sorts of nested message handling behaviors. Which means, since we're trying to keep track of like what order things are happening in some arbitrarily complex control flow, the direction we're going to go is an effect system. So effects have kind of a mixed reputation because we tend to have effect systems that are either small and pretty concise, like Java's checked exceptions, right? Pretty easy to understand what they're specifying, or things that are incredibly complex at the high end of the complexity scale, like if you try to apply session types to a million lines of code. We clearly want to land somewhere in between. But the fact that we have done half of the work with capabilities means we need to do less work with the effects And in fact, our effects don't need to talk about actual communication. They only need to talk about receives and actions within an actor. So the two things we need to keep track of are when a process sort of creates new obligations to itself. So the idea we're trying to preserve is if there's an outstanding PID to send something to a process, that process is expecting to get those messages in the order that capability says they can be sent. And this comes up when an actor creates a self-reference, right? So earlier I gave this slightly simplified picture of you get this one original actor ref, and like vampires, they're all descended from this original, right? But that's not actually what happens, because a lot of them come from that original, but a lot of them also sort of spontaneously come into existence out of the ether through actor self-references. And then we also need to keep track of what order what order the actor attempts to handle messages in, what order it's ready to handle messages in. And so this is something that needs to be totally added. The self-tracking we need to embellish from early versions of this idea. So if we want to talk about what this looks like, let's talk about handling effects, right? So in general, you can have any non-zero number of clauses in a receive, right? From 1 to any, however much you're willing to type. But we'll just talk about 2 clauses for now. Just keep it simple, and the generalization kind of makes sense from here. So the general idea here is that the receive starts looking at the first message in the mailbox and sees if it matches any of these patterns. So conceptually, whatever pattern 1 is, and by that I mean both a pattern and a guard that I'm not writing here, it's going to handle whatever types that pattern matches, followed by whatever is handled by receives nested inside E1, inside that first branch. And then the second branch is similar. It'll handle a slightly different set of types, those that the pattern matches that aren't handled by pattern 1, followed by whatever receives happen in E2. So if we abstract this as saying, well, pattern 1 is going to match a certain type, right? And when I say type here, I don't just mean something trivial like one of these atom singleton types. It could be some arbitrary union or intersection that is matched here. And then E1 handles L1. And pattern 2 matches some other type, and then E2 handles some sequence of messages. Then together, they kind of sort of do this, right? We're either handling a T followed by what the first branch handles, or we're handling a U followed by what the second branch handles. But again, there's a catch. So this is actually the right intuition for what you can get away with in Akka. But that's, again, because in Akka, effectively what's happening is these receives are sort of almost always in tail position, which is not what is happening in Elixir. The catch is that E1 and E2 may return, or they may just run forever. And this depends on the structure of the program. Sometimes we will receive inline to do something very quickly, and sometimes we run a bunch of code and then basically finish by calling receive, and then there's tail calls to other handlers inside those branches. So we need to account for differences in fall-through behavior, which I'll write as a language of handled messages H with no adornment, versus cases where the sequences of messages handled are supposed to cover like all the rest of execution, which I'll add a little up arrow for, right, running to the end. Now, in general, you could have E1 return and E2 run forever. And of course, this becomes very hard to reason about. I haven't seen this happen much in the Elixir code that I've looked at. All right, I won't touch that cable. I haven't seen this happen a lot in Elixir code I've looked at. So for now, we're relying on the assumption that usually either all of the branches fall through, or all of the branches are in this tail position and they're supposed to cover the rest of the actor's execution. So for now, we end up needing to do 2 slightly different type rules for both of these different scenarios. The other thing we have to keep track of is, again, these obligations, right? So I said initially, basically, the first actor ref, or PID, to a newly spawned process has to agree with whatever the initial code is ready to handle. And that's relatively easy to check. So if we know, for example, that the code for this thread that we're spawning is going to handle a certain number of things, and that covers all of its execution, then clearly those are the things that we're allowed to send up front, right? So we get back a PID that lets us send exactly what we know the process is ready to handle. Right? The catch is we have this problem of dynamically committing to handle new messages by creating a new self-reference and sending that out somewhere, and somebody is now going to use that to send more messages. And that is not handled by our splitting stuff we talked about earlier because it's not coming from an existing actor ref. So conceptually, we need something like this. Technically, we need two variants of this, but I'm going to simplify it to one to sort of talk about the key ideas. So the idea is, if we create a new self-reference, this is now a new outstanding PID pointing to this process, and whatever sequences we think are allowable to send through this PID, we better be ready to handle them. So we need to remember that. So we're going to keep track of that as a bunch of commitments. Right? Now, technically, there's a distinction we need to make that I'm not making in the slides between commitments we expect to handle immediately and commitments we expect to handle later, arbitrarily later. So there's a little ambiguity that I'm glossing over here. And the other thing that we need to deal with is also this fact that if we want to avoid really silly deadlocks, we also need to keep track of not just when we create these PIDs, but also when they escape the process, i.e. when they go to the send primitive. Because until they go to the send primitive, either as a target for a process messaging itself, or as part of a message payload sent to another actor, nobody's actually going to send those things. Right? So it would be kind of silly to like just create the PID and then immediately wait for messages that are never going to arrive. Right? So we want to rule those out, and that check, which we technically don't need for soundness, but that's kind of a silly bug to enable, we need to split whether something's actually escaped. So we end up having a few classes of effects, which I'm simplifying here to 3. So we have sequences of messages that the code will handle either in a sort of length-limited way. So for these inline receives, like in the middle of some larger block of code, we expect those all to return. We expect them to be sort of fixed finite sequences. This seems to cover most of the use cases I've seen. Or executions of message sequences that are supposed to cover all the rest of the actor's execution till the end of time, or at least until it terminates or fails. And at the same time, we have commitments, right? Which again, technically will come in 2 varieties. But these are commitments the code has created to itself that we need to check that it actually is prepared for, that it will actually process these messages later. As long as they're not things that it's internally already resolved. So we'll see examples in a second of cases where we sort of create an obligation, satisfy it immediately, and then move on. And we don't want to expose that as a set of messages we're ready to handle, because by the time execution's done, we've already handled them. So I will quickly note, if we commit ourselves to multiple things, if we send a whole bunch of PIDs all at once, we've now got multiple PIDs that might be used in any arbitrary interleaved order. So we take those commitments and we just shuffle them together into one commitment. And that captures what we need. The thing that gets tricky is idioms like this. So in Elixir and Erlang, well, I mean, technically this is a beam thing. It's common in these languages to send a message and then basically like immediately wait for a response to that message. And this is in fact exactly how the synchronous call mechanism works inside OTP. And it's common enough that the beam VM actually specifically optimizes to make this fast, because normally this reply would come in way at the end of the mailbox, and that receive would be slow. So we want to handle this, but we also want to do this modularly, because it's possible for a little extra stuff to be in there, and we don't want to build something that's like super brittle to like, oh, you stuck a log statement in there, and now we can't reason about it, right? So we want to type these separately, which means they have their own effects, and these effects have to combine. So I'm using the little caret here sort of as an ASCII up arrow. So conceptually, this send commits us to handle a reply, and then we immediately try to handle the reply sort of right away. And we want to support this. We want to match these up. And this gets complicated because for different classes of commitments, we might run code that immediately handles the whole thing. We might, especially if we're doing modular incremental checking of different sub-expressions, effectively combine this with code that handles just a prefix or some subset of our obligations, but not all of them. Like if we commit to handling 2 messages in sequence, and then we handle 1, we can only handle 1 at a time, so there's a moment in time where we need to handle what's left. And we may run code that handles only unrelated things, right? Or we might run code that does some mishmash of all of these things simultaneously, right? And so for now, we're working with 3.5 ways to combine these things for later commitment. So we might have cases where some commitments are followed immediately by some finite message handling. We might have cases where that finite message handling is actually unrelated to the commitments that we're talking about. And so we kind of want to keep track of those commitments flowing on. By unrelated here, I mean like the messages have nothing in common, right? Like the code after this expects to handle message A, and the commitment is for message B, like they're totally orthogonal. They can just shift past each other. Or cases where we need to make sure that actually all of the commitments are really resolved because we're just jumping into this thing that's like all the rest of the execution. There's nothing after it, so we need to make sure that all of the commitments really happen. So turns out this slide actually looked quite different 2 days ago because I found a subtle bug in the proof. So this is not full coverage. There are definitely programming patterns that these scenarios don't fully cover. They cover the most important ones, but I'm more confident that this is sound. I do not believe it is as complete as we want it to be. So there's definitely more work to do here. So how do we solve these things? Well, the one in the middle is actually pretty easy. The one in the middle is just kind of like you just push the commitments and the handling past each other because they're not related, right? So you push the commitments later. So we're going to talk about 1 and 3 in a little more detail, right? We're going to talk about handling prefixes, which might include all of them. And we might deal with cases where we need to make sure really all of these commitments are really, truly handled in the future. So one of the sort of other subtexts in this talk is we keep going back to the well of formal language theory and drinking from the well of formal language theory. So we're going to do that again. And there's this other language operation that it turns out they used to teach. It was part of the ACM curriculum back in the 60s, back when computer scientists were really more mathematicians. Turns out this is like a residuated semigroup kind of thing. So this is the quotient of formal languages. It's kind of a generalization of the derivative. And so the quotient of y by x in this direction basically is the set of sequences that you could sequence after some element of x, not necessarily after all of the elements of x, just some. There's at least one thing in that possible prefix x that would get you something in y. So if y is the set of commitments that we actually want to handle, and x is the things we're trying to handle right now so far, this kind of tells us what do we have to do in the future to cover all of our bases and eventually make sure we cover all of our commitments. So if we're committed to handling A and B in either order, so I'm using the shuffle in the expression here. It turns out for regular languages, that gets you something like exponentially more succinct regular expressions. And then we handle A or B, right? We write a receive that matches on A and matches on B and has 2 branches that don't do any more receives. Well, the question is, what do we still have to handle to make sure we eventually handle the other piece of this order, right? Well, what we want is to be forced to handle A or B again. Because if we got an A the first time, we got to be ready for a B. And if we got a B the first time, we have to be ready for an A. But we don't want to weigh the system down with a lot of complicated tracking about, like, under this circumstance, we know we got an A in the past, so we do this. Under this circumstance, type systems get extremely heavyweight when we go that route. So turns out this quotient is just what we need. So if we're trying to handle A and B in either order, and we handle either one of them just once, this quotient tells us, hey, you need to handle either one. Turns out this is an over-approximation, right? Because we could instead write a handler that handles a B, and in that B branch handles an A, and so forth, and get something a little more precise. So this is a sound over-approximation if we're using sort of more relaxed control flow. To deal with some of these other cases, especially the one where we need to deal with, like, we have some commitments, and we're about to, like, make a tail call to some other code that's supposed to run forever and be the rest of our process execution, how do we know that we're actually handling all of those things? And what leftover handling capacity is there to, say, form the top-level handling set of a whole thread? So we go back to the well of formal language theory and drink even more deeply, go into the really obscure back catalog, and find this operation called the scattered deletion of formal languages. So this is kind of this funny operation. I'm not going to spend too much time on it because it took me a while to wrap my head around it. It's kind of weird. The idea is this is the language that you get by finding all the strings in L1 that contain as subsequences words of L2, throw away all the words that have nothing to do with L2, and then rip out those subsequences from L2, and whatever you have left are basically things you could shuffle back together with L2 to get something that was in L1. But of course, when you look at this at the whole language level, this is sort of like a partial unshuffling, right? So you're going to drop some things that didn't arise from shuffling, and you're going to also, ignore the fact that there might be stuff in L2 that's not represented at all in L1, right? So this works even if L2 was not shuffled into L1. Turns out, this is a pretty good description of sort of what's left over after handling a certain set of commitments. So if we take whatever we're going to handle in the future and we unshuffle the things we're trying to commit to, whatever's left describes, what can flow up and be the top-level handling behavior of the thread when we know that we actually covered everything in C, right? So we actually have to do this side check to say, well, yeah, we can do this unshuffle, but this works even if not everything in C was happening in H. So we need to sort of pull it out, shuffle it back in, and see that we got the expected result to make sure that we're actually covering everything we need to. So this is where we are right now. But let's talk about the direction we're going, right? The goal is OTP, which is kind of a weird goal, because as some of you have probably noticed and are maybe scratching your heads at home, OTP is not implemented in Elixir, but I'm building a tool for Elixir, right? So OTP is implemented in Erlang because it predates the public release of Erlang. But it could be implemented in Elixir, right? As the Elixir folks are quick to point out, semantically, Elixir is a superset of Erlang's behaviors. The compiler actually uses Erlang ASTs internally. And so we can imagine re-implementing OTP or large chunks of it in Elixir for two purposes. One, we want to give consistent types to OTP interfaces, right? A big part of the reason people pick up Erlang and Elixir or any other Beam language is to use OTP. So we really want to be able to extend these guarantees to that kind of interface. But of course, these are sort of subtle behavioral types, right? And anytime we look at some fancy library building a type system and we're like, I'm not going to type check the internals. I'm just going to assume I can precisely describe the behavior of the library using my specifications. Usually we get it wrong, frankly. There's always some corner case that's either easy to overlook or just not documented at all, or is technically a bug, but people do it because it works for them, right? And so we really do want to ground types for even sophisticated libraries in real checking about the actual program. And second, doing this is kind of a benchmark for how well have we covered the fundamentals of the language. Because if we could type check a reimplementation of OTP, then we can actually type check similar abstractions that people build as well, not to mention abstractions built on top of a mix of OTP and other primitives like Phoenix PubSub. So to talk about that, let's talk about some other pieces of Elixir that we also need to fit into this framework, and most of them seem to fit in pretty well. So the Beam VM that Elixir and Erlang and other languages run on has this notion of linked processes. And so the idea is if a bunch of processes are linked, they're sort of effectively one functional unit. If one of them fails, they are all terminated, even if they didn't have a local error, unless you set this flag. If you set this flag, then if you fail, you failed. But if one of your linked processes fails, instead of you being terminated, you get a notification, which arrives as a message, which means when we call this, we're obligating ourselves to handle more messages in the future. And in general, we're obligating ourselves to handle any number of these notifications, because if 27 linked processes get terminated all at once, we get one notification, but this process keeps running, and it might start more processes which are also linked, and so on and so on. There's also more precise APIs like process.monitor, where you can say, here's the PID of a process I want to keep an eye on. And in that case, you'll get exactly one notification if it fails. If you're doing this with a whole lot of processes or multiple processes, all of these notification types are kind of going to be intermingled. So if we wanted to be a little more precise, we could imagine throwing in additional singleton types for references, which we're going to hear more about later today, or pushing in the direction of something like a refinement type to constrain what these notifications are for. So this is the basis on which restarts are implemented. Basically, a supervisor monitors somehow one of these processes, and when it gets a notification, it'll start a new process. So what happens there? Let's say we have a PID that lets us send these two messages in some order, and we send one, leaving us with the ability to send the second message, as we would expect. But in the meantime, the recipient crashes after getting that first message, and we don't know that, and we send the message anyways. What happens? Nothing, really. The message just kind of goes away. This is fine, because we're not doing OTP yet. Nothing's restarting the process, right? The sender is still sending things in the order it was supposed to. The now terminated process has stopped trying to receive things, so it's actually OK. So OTP is where most Erlang and Elixir programs get their supervision and restarts from. And restarts is something I kind of often want to put in scare quotes, because it's not exactly a restart of the same process. It's the spawn of a brand new functional replacement for the process that failed. So they're really more substitutions under a handle. OTP allows you to send messages to basically a name. Really, it's an atom. But effectively, you can register names for your processes and then send through that name instead of a PID. And what a restart really does is it registers a new process under the old name. Sends via PIDs don't reroute. Sends via name, if it's been registered, do actually reroute. So we need some richer capability types to do similar PID-style checking for names that we know are associated with processes as well. So that's simple enough to add to the context of a type system. Technically, this all bottoms out in another virtual machine API, process.register, that actually is the way a name becomes associated with a process, right? And so it turns out we'll need to impose restrictions on what we register processes as. And the other thing that we need to deal with is that the replacement, if the client is sending a bunch of stuff via name and getting rerouted, it might not get the start and complete start of a valid prefix, it might get the tail of a valid prefix. And so we need some way of dealing with that. And it turns out these actually seem to fall out of existing machinery that we've already been building up. So if we want to say have a gen server, this is sort of the most common, or at least most well-known actor abstraction in OTP. Well, since name lookups are allowed, any part of the program can now also summon a PID, effectively, summon a handle to this process at any time, anywhere, as many times as it wants. So we want this type to be self-splitting. We want it to be the case that if you have permission to send to L, you could do this as many times as you want, because this is effectively what happens inside the VM when you send to a name. It looks up, makes a copy of that same PID that it has stored, and hands it off, expecting it to be used the same way as any other copy it's handed out previously. So we need to be able to mint infinite copies at the same type so we can impose that restriction. Then on the server side, what we effectively need is suffix closure of the message handling, right? So suffix closure is this property where a language is suffix closed if for any word in the language, if you take away some prefix, that suffix is still in the language. And so this is how we get to the point of forcing a server that is going to be restarted and replaced to handle picking up and taking over after its predecessor has failed, right? So it might not handle these messages in exactly the same way. It might, for example, say, hey, sorry, I'm the new guy. Can you fill me in, right? And ask for more feedback rather than like continuing on because it probably lost state. But this means that we can give senders sort of the familiar API. The senders don't need to worry about, oh, am I sending in the middle of the protocol when there is a restart? It can be transparent on their side. But the type system will force the recipient to actually be tolerant to getting receipt of late messages from a predecessor. The last thing I want to talk about that's also kind of an interesting challenge is the practice of wrapping messages. So a lot of libraries for building distributed systems, and OTP does this extensively, what they do is they expose an API that the application uses to send messages, and separately APIs to receive the messages, but internally it doesn't actually send just that message. It sends a package that contains it. So if we distill OTP gen servers down and down and down until they fit on a slide, you might get something like this, where basically there's essentially these two client APIs up here, cast for asynchronous sends and call for a synchronous send and wait for a response. And then the private actor state basically looks at what comes in and it dispatches to application-specific callbacks, handle cast, handle call. And you'll notice that the clients, they receive a message, the client APIs, but they actually wrap it up inside another structure and send that over. And then the recipient gets the same matching things and unwraps it. So the application never sees the wrapper. So it'd be kind of weird if it had to deal with types that talked about those details. And especially weird if like those details changed like between releases. That would be pretty gnarly. We don't want that. So there's a lot of abstractions like this, including like PubSub, that wrap other messages. And when you talk about like retries and failure tolerance, sometimes they inject other messages as well. So we need some tools to relate sequences to other sequences, right? We have tools to relate sequences to other sequences. If you were thinking I was going to bring AI into this, I got you. We're going to use transducers, right? So formal language theory has this established toolkit for relating sequences to other sequences. They're transducers. They're essentially, you can think of them as a state machine that has both input and output, right? And so basically, if it can generate a certain output string for a certain input string, this is sort of the relation that is being modeled. If you have non-deterministic transducers, then this is really a relation and not a function, right? And these have lots of nice properties, especially if you do regular, i.e. finite state transducers. Because if you take the rational regular transduction of a regular language, you get a regular language. Some of the operations I've talked about don't really work well with context-free languages, but if they did, turns out there's a lot of language classes beyond regular languages that are also closed under this relationship. So regular transduction seems like the right toolkit to bring to bear to sort of expand the protocol going into the library internals and then hide it again going back into application code because they're often reversible. And they can be expressed in a form that's a lot like a regex, or there's some nice DSLs, and Elixir is very good for implementing little DSLs. So that's where we're going. But longer term, I want to talk about adoption, right? Which is maybe premature for a project that I have not released anything publicly for yet. The source code is just private to me right now. But this is sort of the end goal, so we have to plan for it from the beginning, right? It's very easy to build things that like work in the sense of like, I checked the property, I got the guarantees that I wanted, I personally, as the creator, am able to use it, right? And of course, I'm having fun. Like, all this stuff is pretty cool. You can tell that I'm fond of formal language theory, probably. I think that comes across. But I think anytime we're doing research, it's important to think about, is this plausible to adopt? Sometimes the answer is no, and if you have a good reason for that, there are lots of good reasons for the answer to be no. But if we're thinking in the direction of like, hey, we want to provide guarantees to real programs, then we need to think about like, what's the envisioned way to get there? So I think this is on a trajectory that, once it's finished, is going to be in the right ballpark. Obviously, if you disagree, let's talk, because I actually do want to build something useful. And the key here, I think, is incremental adoption, which is something that we overlook in the PL community kind of regularly. We'll design things that are supposed to layer on top of an existing language, but if you don't convert your whole 5 million line program all at once, you don't actually get any of the guarantees, right? This is one of the lessons that the gradual typing folks, of course, have learned very well. As well as, of course, lots of the other work on set theoretic types and related things that we've heard about from the Erlang community. So these accurate capabilities, this point of view where we have PIDs that talk about the sequences you're allowed to send through that individual PID, you can do that by itself, right? The effect system stuff we were talking about to do the receive side checking, you don't need that for the sender side checking to work. And even that is sort of another layer of incremental, because you can embed just the upper bound on messages in the language thing, and you can embed the way things are done right now into that, right, as I said earlier. So this means that there are small stepping stones to incrementally get a little more, a little more, a little more guarantees. And again, this gives us some guarantees about behavior and where to look for certain kinds of bugs, even without the receive side checking. The other thing is, because the effect checking is just looking at one actor by itself at a time, we can check one actor's effects without worrying about whether the other actors are checked for receive effects at all. And then our guarantees only apply to the one actor we are checking receive side properties for, but that's okay, right? As long as all the incoming PIDs, which are in the rest of the program, are using this capability system, right? So that means that there are migration paths where we pick our favorite actor, and we start incrementally refining its incoming PIDs to use these protocols. Then at some point, if we have some actors past that step of migration, we could then look at checking their receive behaviors. But this can progress at different paces and even stop at different points in time for different parts of the program, right? So this is something you don't have to do the entire program with. You can sort of opt in as you go. So wrapping up, I hope I've at least, if nothing else, convinced you that capabilities are a useful, powerful way of looking at the world that still have some tricks up their sleeves, even though they've been around since the 60s. that mixing capabilities with effect tracking can be even more powerful, and also just mixing different techniques together, if they play nicely together, gives you some more incremental usage scenarios. You can get a lot of strong guarantees without getting anything too heavyweight, and of course heavyweight is kind of subjective here, but I think this is definitely lighter weight than other things that we have. And if nothing else, go try your hand at Elixir. I think it's pretty fun. That's it. Thanks.
So I am looking at the Discord channel and I'm not seeing any questions posted there. So questions here. Yes.
Okay, thanks for the talk. This was great. Really
Thank
fun.
you.
I'm not sure I believe you about the incremental adoption. I think that would work if you've got like a topological order on the actors. But I'm worried about the case where one actor's talking with another, but then that first actor is communicating with somebody else as part of the protocol.
Okay. So I guess maybe I could be clearer about exactly what we're checking about the receive side behaviors, which is that the recipient will never try to handle a message in an out of order with the order they were sent. Now, this is a subtle guarantee because it means it depends on the other actor's liveness properties. It depends on them continuing to send messages. So certainly if some other actor runs off and gets stuck in an infinite loop, and we for example, if we try to deal with, okay, apparently I don't know where that slide went. Trying to find the one where we handle a self type and then, oh, it's right, it's way down here. All right, yes, here we go. So cases like this, right? Like, if we send that off, and then that one actor never gets back to us, like, we're stuck, right? So most of the time, there'd be a timeout there, and I'm not talking about timeouts, and I think that's another important direction to go. But I'm not guaranteeing that the actor is not going to get stuck here. I'm not guaranteeing deadlock freedom.
Okay, yes. I've got two other questions, but I can share.
Could you go back to the splitting slide?
Yeah.
I think, and maybe I should have asked this question in place. I was a little bit confused about that because I wasn't clear how you were handling ordering.
Handling ordering?
Yes. So the definition of L, and so the definition of that operation there allowed interleavings, right? If I have, let's say, I have message A and then I have message B, and if I split that up into two variables, could I not use the second variable to send B first? Or are your contexts?
In this setting, no. You have to pick which one is going to be used for that, right? So is there code that maybe makes copies that maybe it doesn't strictly need to, and then kind of alternates back and forth?
How do you enforce
Yes.
that in the type system? Because are the contexts ordered in some way? How do I know that I've used X before Y?
Well, actually, that's exactly the point of this, is we don't need to worry about that. So I do have ideas where if we do actually want to enforce something like that, there's some other tricks that we could talk about offline that are a little more subtle that we could shoehorn that in. But this rule says we don't have to care. Because when we create that alias Y from the original X, if X's type was originally this PID L, we are changing its type to this L prime and its new copy to L double prime. And this shuffling models the fact that we don't know or care what order those two aliases are going to be used.
Right, so this is only going to be allowed when we don't have very much sequencing. This is going to work if we can handle messages.
Yeah, I mean, if you have, so if you have a PID that says you are allowed to send one sequence of messages, and it must be A, B, C, D, E.
Then we just can't.
There's not.
Okay.
You can split off the empty capability,
Right.
which is still useful for certain APIs like monitoring and receive and stuff. But yes, you would have to sort of follow your one chosen copy through.
Sounds good. Thanks.
So this has been bothering me since the beginning of the talk, but how do we know
Uh-oh.
regular languages are the right abstraction for protocols? It seems like a very session-type view of the world, which is now pasted it onto Erlang. But why not context-free? Why not something else?
So there's two sides. So, all right. There's the technical side, and there's the informal, not backed by human studies, opinionated side. The formal side is, well, I'm throwing all these language operations around, so we kind of want a class that's closed under all of them, and the regular languages are. So there's the it works argument. There's also the side of, so I've actually been teaching theory of computation the past few years. And the gap for people to build their intuition, people seem to get intuition for regular languages pretty easily. But building intuition for context-free languages seems to be something that only compiler and PL people get really good at, from what I've seen, right? And of course, there's the chicken and the egg problem. Like, if there's a tool that works on those foundations, would people invest more time and spend more time and develop stronger mental models? Perhaps. I'm intentionally being not totally committal. Like, I'm not personally opinionated. I would love to find a more expressive class of languages that worked with all of these operations. I'm not opposed to that. But what's not in the talk is that we're skirting very close to a number of undecidable properties here. Like, so when I talked about the, I always want to call it shuffle traction. But when we talk about like this operation, scatter deletion, right? This is sort of dancing around the idea that if I give you a random regular language, it's currently unknown. If I give you the language, can you find a non-trivial decomposition into two languages that shuffle together to give you that regular language? We don't know if it's solvable. It's an unknown, unanswered problem. We don't know if it's even undecidable. But we're sort of skirting around that because we're in the context of we always start with we have kind of a candidate in mind, and then we can do this scattered deletion. So I would love to find another more expressive class of languages that works with this. I have other work where I'm playing with such classes of languages, but there's a lot of unknowns.
Yeah, okay, that sounds great. It does seem like something funny is going on, though, because people write protocols in practice, even if they don't understand context-free languages at a deep level.
Yeah, I mean, there's definitely some of this is like surface syntax, like context-free grammars are themselves not the most intuitive. Thinking about PDAs is not intuitive. But thinking about call and return, right? And so this is one of these things that makes me think, like, should I go dig around and see what happens if we look at like visibly pushed down languages or other classes that are supposed to capture some of the nice properties of context-free languages without losing some of the things you lose from regular languages? There's a lot of interesting questions to answer there for sure.
Okay, last question about the types that we saw don't say anything about the payload of a message, if I was following correctly. Right, do we want to see something about the payload in the future?
Yeah, and so my answer to that is, over the years, I've worked on various sort of twists on hacking refinement types into things. And so that's kind of my inclination here. But frankly, I want to spend more time playing with those APIs to build a sense of whether that's really the right call. Like I floated the example with the process register, where we could give more precise types to the notification message that would come in later if we did have refinement types. So there's definitely opportunities there, but I'm not sure if that's the whole solution or not, right? Or the right solution or not.
There might be a genuine challenge if, depending on the payload of a message I receive, I choose what path to go down next. in the communication?
Yeah. So I am using, as a framework for the effect tracking here, effect quantales, which is another one of my own creations. And those are, I mean, that framework was designed to model the sort of typical class of flow-sensitive effect systems that's insensitive to values determining the branch, right? So basically branching is treated as non-determinism. And that's what we're doing here. And that is sort of a calculated risk, I guess you could say. I'm not opposed to adding richer support for that, but I'd rather build something that works and then see where it falls over and then learn from that to figure out, because I have less of an intuition for exactly what form that should take here.
So my question is going to expose my current thinking.
Sure.
What I'm
We're all thinking.
Well, I try not to think. It gets me in trouble.
It's true.
So when I've got an effect, and this effect is tied to an external device,
Mm-hmm.
And I want to poke the register of that external, very often it matters very strongly what order
Oh, yes.
I poke those.
Yes.
And so what I'm thinking is, if I've got an actor sitting in front of the access to be able to poke that,
Yep.
then I need to be able to control the order of the data that's being pushed into those register,
Yes.
that register or register.
Yes.
And that's really hard to do in something like C.
Oh, yeah.
Yeah, I mean, you just, and it's why we have issues. And so I've been considering you doing something along these lines that you're describing, without the splitting, not necessarily reshuffling even, just how do I control that? It seems like that's part, like the simplest version of what you're talking about.
It depends on kind of where you think the right solution to the problem is, right? And so I presented this framework that I'm fleshing out that, reveals my own biases about where I think the right places to interpose and approach to interpose is. But it kind of depends on, do you want to build an actor that is robust to confused client programs, telling it to poke registers in the wrong order? In which case you really want to reason about the internal checks that the actor is doing to check that it's doing a reasonable ordering that the hardware won't freak out about. Or do you want to sort of trust this actor and push the restrictions off on the senders? So my framework is very much in the latter spirit. We want to push more of those restrictions off on the senders. But it's not illegitimate, of course, to say, like, you know what, I want to build something that, send me whatever you got. I don't care if you're wrong, I'll just tell you you're wrong, and then internally make sure you get those checks right. So you could apply some flow-sensitive effects checking to that. You would need probably dependent effects to reason about those values. But that's definitely a direction you could go. It would work. It'd be interesting.
Thank you very much.
Thank you.
Again, I haven't seen any new questions come in on the Discord channel. So I guess we're good.
All right. Thanks, everybody.
Thank you very much. Our next presentation starts at, 11? Yeah, so we have a coffee break at 10:30. So we can go do that, and then we'll be back at 11. So thank you.
Hello, hello.
Hello.
Hello, Daniel. Oh, we are running a little bit behind the schedule. We'll let you know when we start the session.
All right.
Yep.
Thank you.
Welcome back. Daniel Lucas. He's an assistant professor at Eötvös Loránd University in Budapest. His research includes programming language static analysis, formal verification, model checking, and Erlang and Beam bytecode. And Daniel will present a mechanized semantics of Erlang's references. Please welcome Daniel Lucas.
Thank you very much for the nice introduction. Can you see my slides?
Yes.
Perfect. Thank you very much. Welcome, everyone. It's nice to be here with you. The title of my talk is A Mechanized Semantics of Erlang's Differences. I am Daniel Lukács once again, and my co-authors are Péter Berecki and Daniel Horpácsi. We are all from ELTE University, Hungary. Let me just quickly start with an introduction. We are all from the High Assurance Refactoring project from ELTE University. Basically, we are developing a formal verification infrastructure that you can use to prove specification properties about your Erlang programs, Erlang refactorings, and recently even an Erlang. We are developing a certified Erlang compiler as well. And for this, we are relying on the raw proof assistant. I don't know how familiar you are with this tool. This is basically something like a programming language, and you can write theorems and prove those theorems in the same way you would write a computer program. And in the rest of the talk, sometimes I will say formal verification or formal semantics. Sometimes I will say machine verification or verification, mechanical semantics, and formal verification, formal semantics interchangeably, because in ROC, the computer, you can use the computer to basically verify programs and check your proofs. And the central component of HARP is so-called mechanized semantics of core Erlang, which was developed by Péter Berecki. I will talk about this later in more detail, but for now, just to explain the title, my goal was here, or our goal in this current work was to extend this core Erlang semantics with unique references. Just a few words about why formal verification still matters, or maybe matters even more than before. Currently, the current best practice is testing, but we all know, we all heard already that testing is only good for proving the presence of bugs. It cannot prove the absence of the bugs, while formal verification can also prove the absence of bugs. And the reason people still don't really use it is because many are considering it inflexible in practice. It requires a considerable overhead to, for example, proofs every time you write a new function in a programming language. But this is recently changing, as I see, with the emergence of AI. On one hand, you probably heard the stories about people using AI to find security holes, generate exploits. And on the other hand, AI also makes it more practical, more available for you to use formal verification tools, including ROC. For example, you can use AI to generate a proof of a theorem, and sometimes this can lower the time requirement from a few days of, let's say, proving a theorem, from a few days to a few hours. Okay, so let's start talking about references. You probably have already met with references, but just in case, a references is a unique term in Erlang. Most often we are using references to identify messages and responses to our messages. That's why it's important that they are unique. Basically, there are two important operations you need to know about references. One is this makeref function, which is commonly used to create references, and the other is comparison for equality, when you check whether, let's say, the reference you received is the one you had already. And there are a few other functions that we could talk about, but we discussed those in the paper. I won't mention them at the moment. In this presentation, I will show only this single piece of source code, so please don't worry too much about it. But I would like to ask you to study this piece of code a little bit. Basically, what you see here is that we have a function called putMap that expects a value and a map. And this function basically simulates a database by creating a unique key for this value, and then stores the key and the value inside that map. And the way it creates this unique key is using, of course, the makeref function. And later in the code, let's say in the main function, we are using this putMap function to put a value in an empty map, and then later on we put a different value, this b, in that same map that we used earlier. And basically the question we should ask here is, how do we know that putMap will not overwrite the old value with the new value? And well, the simple answer is that we assume that the key, this makeref function creates is a unique key each time we call it. And so since the first value and the second value will get each get its own key, we know that they will get different keys and will not overwrite. Okay, but please notice that that I said that we assume that makeref returns a unique value. Why can we assume this? Well, the best answer would be, or we could say, is that we looked it up in the Erlang specification. Unfortunately, Erlang does not have an official specification. It does have an implementation, it does have documentation, but not an official specification. I guess we are familiar about what kind of problems can come from this. But even if there was an official specification that we as programmers can check and look up, it would be it's still an erroneous process, and I would say it would be still better if somehow the computer could tell you that, in fact, based on the code that you wrote, the property, let's say this property about overwriting or not overwriting, will be satisfied, or the opposite, it will not be satisfied and your code is unsafe. It would be much better if this could be done automatically. And basically, this is the goal we have in the HARP project, and this is the goal of the core Erlang semantics as well, to enable such an automatism that can tell you things about your programs, important, useful things about your programs automatically. So next, I would like to give you a quick introduction to this core Erlang semantics, since the work that we were working on is based on this one. I try to keep it a very high level. I will not talk about these details. You can find them in the papers. I would just like to tell you that basically the semantics of core Erlang consists of evaluation rules. These rules are expressed in a formal syntax. And I would like to give you a little introduction about how these rules actually work. Basically, the task that the semantics solves, to simplify a little bit, is it describes how can we evaluate an expression. For example, the expression that you see here, 1 plus 2. Since this formal semantics is a so-called reduction context semantics, the way it works, the way each rules are described is that these rules split the syntax tree of the extraction that you want to evaluate into two parts, into an evaluation context and into a regex, a smaller subtree, which is called the regex. And basically, the way these rules work is that they do this splitting, then they simplify, or let's say reduce the regex into a simpler, smaller expression. And the way they do this reduction is that they can consider the evaluation context, so the upper layers of the tree around this regex, and in the end of the process, we hopefully get the normal form result of the evaluation. In the case of 1 plus 2, it's 3. And I have a small animation for this, just so you can see how these rules work in progress. One thing you need to consider is that when we call a function, including the plus function, there are actually a lot of things are happening that we do not talk or do not think about, but the semantics needs to describe this very precisely. One of these things, for example, is the order of evaluation. And in the case of Erlang, that's actually relatively complicated topic because before you do anything, you have to first evaluate the module name of a function call. Then you have to evaluate, when this is done, you have to evaluate the function name. And each of these cases, the rules select the thing to evaluate. They do the evaluation in considering the context in which we are doing the evaluation, and then once the evaluation is done, they put back the reduced term in the original place. So once again, module name, function name, then you have to evaluate the arguments themselves. And once everything is done, that's when you can actually call the function that does the actual evaluation, the actual work. So this is about the formal semantics. If you remember one thing, it should be the evaluation context and the redux. And now I would like to start talking about our work regarding the semantics of references. Basically, when we ask how to formalize references, the main problem we have to face is that the Rock language, or the language used by Rock, does not have a way to define unique values directly. And references are unique values, so we need to go down a little bit on the abstraction level. We have to do it ourselves. And well, how to do this? There are multiple ways. One would be to do a faithful representation of the current implementation in the Erlang OTP. But the thing is remember, our goal is to create a formal specification, and for specification purposes, sometimes modeling implementation very closely is more detailed than what is actually needed. Maybe we will never ask things that are there, and it's a considerably difficult task. So we can go with more abstract approaches or more naive approaches, as long as they do what the programmer would expect that they are doing. A second idea, or second idea was to model references as global counters. Basically, whenever a reference is created, we assign it a counter, then we increment the counter, and then the next reference will be created from this incremented counter, and so on and so forth. And this is a completely good idea. The problem is that in the core Erlang semantics, we do not have a concept of global state, and in order to introduce it, we would have needed to change all the semantic rules in the semantics, which would have been considerable work, and even worse, it would have break most proofs in the semantics. Not in super significant ways, but still it would have meant a lot of work to implement references this way. And there are some other approaches where how this can be solved, but it would be a lot of work either way. So we try to come up with a solution that is simpler and requires less work, and this is what I'm going to talk about in details here, and this is what we describe in the paper. It's called injective encoding of configurations. Basically, the idea is that, yeah, of course, references, we can model references as positive numbers. But somehow we also need these references to be unique. So this uniqueness has to come from somewhere. And the core idea here is that we have something that is unique in terminating sequential executions, and this something is the configuration during the evaluation, the program configuration. Basically, the reason for this is because as we evaluate a terminating sequential program, the number of steps until termination will always strictly decrease. So the idea here is that we can use the configurations as the source of uniqueness, and somehow we can encode these configurations into a positive number to get a unique reference. That's the idea in short. And there is an extra point here that when we call the makeref function, on those program points we don't have redexes. They are not part of the configuration. I mean, they're part of the configuration, but they are always empty. We don't have to consider them. It's enough for us to encode the evaluation context, because this is also always going to be unique at the program points where we call the makeref function. So this is why when I will talk about the encoding, I will talk about the evaluation context, but you can think of the whole configuration as well. And one more thing, maybe the most important thing, is that, okay, we have unique evaluation context and we turn these into positive numbers. But there is an important thing here, is that what if that during this transformation we lose the uniqueness? We need to make sure that when we encode the configuration, the resulting value, the resulting reference is also going to be unique. Okay, so in other words, in more mathematical words, what we need is that the encoding function must be injective. So each unique it must map each unique context into a unique positive number. And there were some woodworking type of work you can expect. We have to extend a little bit the core Erlang syntax, a little bit the semantics, but in this case we only have to modify 2 rules, and even there it was only just a smaller modification that did not affect too many other lemmas. It was not a very difficult change, although I will return to this later. What was more difficult is to create an encoding that is injective, and especially proving that in fact the encoding function that we defined is injective. The basic idea of the implementation of this encoding function is that we were lucky, we could use a library of rock called stdpp. It provides a so-called Gen3 data structure, which can encode, which stdp can already encode injectively into positive numbers. And so our only task was to transform our evaluation context into this Gen3 data structure injectively, and then we didn't really have to think, okay, how to turn a syntax tree into a number. stdpp solved this for us. And I'm not going to going into details about the proofs. Proof of this statement that the encoding that we defined is injective. It's a long proof. In Rock, it took more than 1,000 lines to formalize this proof. But in theory, it's not very difficult. We basically just have to use a structural induction on the syntax of core Erlang. If you want to learn more, you can check the paper. And as we near the end of the presentation, I would just like to return to this example and tell you a little bit or show you, demonstrate a little bit how is it actually useful, why did we spend so much time, so much effort on proving this theorem. And for that, I would like to go back here to this code example. Basically now what I can tell you is that when you now look at this example, when we first called the put map, we have been in a evaluation context called K1, and with the above definition of the makeref, we now know that the reference is going to be the encoding of this K1 evaluation context. And similarly, when we do the second call to put map, we are in a different evaluation context since we are now nearing the end of the program, or we are closer to the end of the program. We are in a different evaluation context. And so the reference that this put map created will be the encoding of a different evaluation context. And at this point, we can define a lemma. We did define a lemma in Rock that proves that indeed, when we query the first key in the map, we get the first value that we stored and not the second value. You can see this lemma here. It's a bit compressed, but I can basically just tell you the idea of the proof. The most important thing, as we said, the two evaluation contexts here are different. And since we proved earlier with more than 1,000 lines that the encoding function is injective, we can rely on this fact in the proof and then prove that since the encodings are injective, the references will be different and they will be unique. And since they will be unique, it follows that indeed the value of the first key will indeed be the first value. Again, you can find this proof in the paper as well as in our Rock code. And this is just almost the last slide. Basically, there are some issues and one more serious problem. These two issues, how can we handle non-termination, how can we handle concurrency? There are solutions to this. They are not very serious problems. We do have ideas and we do discuss ideas about them in the paper. There is a more serious problem, on the other hand, which we unfortunately only found out later, that the encoding violates a fairly central lemma in the core Erlang semantics called the frame stack independence lemma. And it would be quite difficult to solve this problem. It would require a major rethinking of the framework. But all is not lost, and I would like to talk just a little bit about how do we plan to proceed even though we run into this obstacle. One thing that I already mentioned is that we are currently working on a certified compiler for Erlang. And there are two things. One is that in this compiler, we will have a task where we will need to encode nodes in the syntax tree to numbers injectively, so that we can later create labels in the Beam code which will be the target output of the compiler. And this is exactly the task that we solved here, and that was like 80% of the effort that we spent here. So the good news is that we will be able to reuse the injective encoding in the compiler. And the other good news is that probably we can go on with the idea about the counters to actually formalize the references in the semantics in the future, because extending the rules is something we will need anyway. And the thing is, I told you it's kind of a laborsome task, but I also mentioned you at the start of the presentation that there is some hope that AI can help with this, because basically these are tasks that are based on the origin, on some existing code. It's a kind of a repetitive kind of work, so it's something that maybe we will be able to use AI for in the future. And that's my final slide. It's just a summary about what we talked about. We extended the formal semantics with references. We used an idea that relies on injective encoding of program configuration. We proved mechanically in ROC that indeed our encoding is injective, and we demonstrated how to use this lemma to reason about more practical programs and the properties about such programs, and we discussed limitations and future work. And with this, I would like to thank you for your attention, and if you have any questions, they are welcome.
Okay. So we don't have any questions on the Discord channel. Do we have any questions? What questions do we have here in person? Okay. All right. Thank you very much, Daniel.
Thank you very much.
All right. Let me get to the right place here. Okay. Our next presenter, the next speaker is Albert Schimpf from the University of Kaiserslautern Landau. Albert's work focuses on bringing stronger syntactic typing to Erlang, and he has been one of the developers of Etilazer. I hope I'm saying that right. The set theoretic type checker for Erlang. Today he's going to present set theoretic type checking of beginning Erlang code, a retrospective study. Please welcome Albert Schimpf.
Welcome everyone, and thank you for having us. My name is Albert Schimpf from the University of Kaiserslautern, and this is joint work with Stefan Wehr from Offenburg and Annette Binuse. Earlier this week at ICFP, we reported what happens when you point a set theoretic type checker at expert Erlang code. Today, we go to the other end of the spectrum. 5 years of Erlang written by students who had just learned the language. First, a short overview of Etilazer. It's a static type checker for Erlang, written in Erlang, built on set theoretic types. It works one top-level function at a time. The function, its spec, and the specs of everything it calls becomes a constraint set, and the solver solves it. The solver is called tallying, a generalized unification over type algebra with union, intersection, and negation. The result is OK or an error. A type error, a non-exhaustive match, or a redundant clause, among other type error classes. The specs it trusts come from OTP, plus our own overlays, and of course the specs from the modules under test. And finally, note that the function with no spec is not an error, it gets the dynamic type. The loop back is the companion report, is the companion experience report. We pointed Analyzer at its own core and managed to verify all of its 29 modules plus 5 OTP modules. This we consider expert code. Everything from here on is the same tool, same settings, but in code written by people who were learning Erlang at the time. This also includes code from myself. Let's go over the type language features that the talk will focus on. Erlang already gives you first-class unions, here in the type alias. It gives you second-class intersections, that is 2 arrows separated by semicolon is Erlang's own syntax for an overloaded spec. And at the meta level, we get difference and therefore negation. The second clause only ever sees what the first clause did not take. So x down there is an integer, and returning OK is exactly what the integer arrow demands. It is implicit in the semantics of the runtime of Erlang. Before we put anything in front of students, the first question is whether the tool would find anything at all. Here are 2 examples, both from code that already passes dialyzer and equalizer. These are 2 lines from our own constraint solver. There are 3 occurrences of the variable st2, which threads state through the solver. The first one binds, the second one does not bind. It is a match against the value already there. So this line quietly asserts that normalize returns the state it was handed, and if it ever does not, the solver crashes with a bad match. What was meant was to thread the updated state through. I made a counting typo basically, and it sat there unnoticed for about as long as the code has existed. Why did we find it? Internally, a match becomes a case expression with a single clause, and exhaustless checking is on by default. The clause for st2 does not match is missing. So subtract what the single clause accepts from the input type, and you will find that the remainder is not empty. The second one is from OTP itself. isSet is spec'd for every term and has a catch-all clause, so it looks total. And when something is total, you may pass any value, including improper lists, which terminate in something other than the empty list. Pass it 1, and the head pattern match is fine, but the 2-argument helper below is only fine for proper lists. Function crashes where it promised you a boolean. This has been in the standard library for 16 years, and it passes dialyzer and it passes equalizer. 2 things hide it. The const pattern is overloaded. It matches proper and improper lists alike. Further, you cannot guard against this either, because isList does not filter out improper lists. It cannot. You would have to walk the whole list to know. Same mechanism as before. Input type minus the clauses, remainder not empty. Both bugs come out of the same feature set, and this is all of it on one slide. The point of putting them together is that you need most of them at the same time. For exhaustless, you need negation, occurrence typing without intersections cannot express what a god told you, and the moment you add complexity cutoffs, a guarantee becomes best effort. Which brings us to the actual questions of this talk. Our students arrive from Java expecting the compiler to catch obvious mistakes. Erlang stays silent, and dialyzer is deliberately conservative, so it stays silent too. Students still ask us for better tooling, especially related to types, repeatedly. Formerly for Erlang, nowadays for Elixir. So we have now 3 questions we want to answer. Is it fast enough to sit inside the student's edit compiler? Is it invasive? How much does the program have to massage the code before the checker stops complaining? And does it drown the user in false positives? 2 of the 3 we can already answer on expert code. Fast enough? Yes. Close to 1000 specs, 0 timeouts, a tenth of a second per function. Full-featured set-theoretic checking was assumed to be too expensive for this, and finally we managed to get the checking time into a tractable range for most use cases. Is it invasive? Actually less than we expected. For example, having exhaustless by default, only 2% of checks needed an opt-out. The expensive part was everything around it. Overlays for standard library specs, downcast at untyped boundaries like ATS tables, splitting oversized functions, and above all, just simply writing the precise enough and sound specs. And by doing that, we found 3 defects in our own code and 18 in the standard library so far. all in code Dialyzer is happy with. So in expert code, we are happy with that. But will this transfer to student code too? This corpus we looked at is a master-level distributed programming course from 2018 to 2022. About 60 group repositories, 1,000 distinct modules after deduplication, and close to 6,000 top-level functions written by students. Since we did not enforce types at the time, the amount of type specs is really low. We only have 14% of functions carrying a spec. That really dampened our expectations to find interesting bugs. Some files we had to drop because they could not get passed. Remember, we talk about basically legacy code with breaking changes happening in the meantime. And that leaves us about 4,600 we actually check. Since a function without a spec gets dynamic, missing annotations should cause no friction at all. We check the code exactly as it was submitted, basically. Beginner Erlang code, especially in the first weeks, can look really strange at times. And I can confidently say that because I was there myself. This is how code looks like if you are arriving from Java. Booleans compared to Booleans, a while loop wearing a recursive costume, a method call on a record field which Erlang does not have. When we later did try to at least suggest using type annotations, it turned to be more difficult for the students to become accustomed to a type first, implementation second design than just staying in the dynamically typed world. We tried things like write functions that fulfill these type annotations. The idea was that reading the intent from the spec should produce the body implementation. Here the first argument is a list of tuples tagged with the atom number, each carrying an actual number. The second argument is any, deliberately. The student had to work out what that second argument could possibly be. We got many different answers over the years, including just implementing the minimal implementation that just satisfies the spec, which can be nonsensical, or even up to pure confusion to where the student couldn't even imagine what this type signature could do that is at all useful. Some managed to get the idea, sometimes already learned a functional language before. To summarize, here's what we naively expected. Almost nothing has a spec, so almost everything is dynamic, therefore roughly 0 defects, maybe some exhaustless false positives, otherwise no signal. And that would have been a perfectly good result. A checker that stays quiet on annotated beginner code is exactly what you want in a classroom. Silence is a feature here. This is what we actually got. 89% of functions check clean. That's nice. 11%, about 500 functions produce an error, and the error split 4 ways. Green, 70%. Genuine type errors, the spec is narrower than the code, or a match is not provably exhausted, or something similar to that. These are usually because the students wrote specs, but did not check against Dialyzer. I think a good chunk of that could be fixed by forcing Dialyzer on them. Orange, idiomatic-leaded crash code, which is not exhaustive. I'll get back to that in a bit. Red, false positives that are out of reach for us. So that's code that would need to be changed or have a cast added or something like that. And gray, another category of false positives which were really suspicious because that was code that we should be able to handle. Where does any of this signal come from if only 14% of student functions carry a spec? Are all errors contained in those 40% of functions? Not really. 14% is the share of student definitions that are annotated. But additionally, the call sites are important. And there 63% result to a specification because students call the OTP constantly, and in OTP, every exported function is specified. So the types come in from the standard library and the contradiction shows up in the student's code. If both sides were dynamic, nothing could ever conflict. We will see one of them in the green block. The good news and question 1 on student code. Student code checks clean and it checks, at least for us, fast. Median is basically milliseconds, 90% under 10th of a second, nothing over half a second except for functions that hit a 15-second budget. This is quite comfortable inside an edit compile loop. You can run this on safe. And one function at a time means a student gets an answer about the function in front of them, not about the program as a whole, which was one specific complaint about Dialyzer in the past, especially with LSB support. As for question 3, the red block, some code is simply out of reach. These two guards partition every possible pair of arguments, so the if can never fail at runtime. We reject it anyway, because we turn a guard into refinement only when it constrains a single variable, and a comparison of two variables is a limitation of the set theoretic framework. All of those together is 0.5% of the functions we checked. The framing we would give students, a type is an approximation, and when it is too coarse, you widen the spec, add an overlay, downcast, mark this non-exhaustive, etc. All three can be taught. A word on exhaustiveness, since it is the setting people expect to hurt in a let-it crash language. In our experience, so far, it does not. We need 2% opt-outs on expert functional code, and interestingly 1.5 on student code only, with gen abstractions included. And in most of those cases, the partiality was already documented in the comment next to the function, and comes for free. Negation types make it a property of the algebra. Subtract what the clauses accept from what can arrive, and ask whether anything is left. But it does fire on idiomatic code though, and this is the orange block. A perfectly normal Erlang line, bind the atom left to whatever the call is expected to return, and if it returns something else, just crash. That's the whole point. But the spec of that call says term, so the match is provably non-exhaustive and we report it. The checker is right, the program is right, what is missing is intent and the checker cannot see intent. There are two ways out. Either the programmer declares it with a special marker, or we guess it with a heuristic, say for OK or error unions. We advocate for the marker as the better option, because totality is usually a property of the function at hand. Now the green block. Type errors, 70% of what we report. First, one of the 73 functions with no spec. A gen server, not one spec in the module, in it seats all 3 fields of the state record. Every handler then matches the one field it touches and returns a freshly built record. Erlang's record defaults quietly reset the other 2 fields to undefined on the way out. And the state degrades, one request at a time, until something matches on VC and crashes. Analyzer reports it at the return, not all records fields given. Strictly, that is a rule about constructing records rather than a type, but it is exactly the check this code needed and it fired with no annotation anywhere in the module. One with spec, and this is from a warm-up exercise. To implement list max, that takes non-empty list of numbers, the student was given the spec and the comment about it. Across 21 submissions, we have the following cases for the empty list case. 0, empty list, atoms empty, error, OK, empty list, 42, -10, with the comment claiming it approximates -2 to the 64th, printing to standard output, throwing exception. The spec as written admits the empty list though, so 6 of those answers violate the spec, 4 satisfy it and contradict the sentence instead. And anyone who dropped the clause gets a missing case. Every one of them is student negotiating with a contract instead of reading it, and nothing checked it. It would be nice to have compile time checks for this. Which leaves the gray block and the strange 43 false positives. The warm-up exercises tell students they may use if expressions. To understand how to use them properly, of course. So they do. Analyzer desugars that into a case, exactly like core Erlang, and the value to pattern match against of that case, that's the scrutiny, is the empty tuple, because there's nothing to pattern match against. Now look at what exhaustless has to work with. The 2 guards between them cover every number, but the guards reference x, and x is bound outside the case. So the checker reasons about the empty tuple, cannot prove the branches are exhaustive, and then reports it. Every one of the 43 is this shape basically. Our first instinct was to fix this properly in the type system by modeling outer-bound variables in general, like it's done in other languages and type systems. We had 3 refinements initially, all firing on this one small function. They don't make sense here, but it's only to showcase the triggers. R4 keeps the ground type of a match-bound variable, y is the singleton 42. R2 notices that y as a pattern is not a fresh binding but an equality test, so the clause's lower bound rises from nothing to 42. And R3 sees that the guard tests is list on L, which the spec already guarantees anyway, so the guard is a tautology. Put together, the single clause covers the scrutiny and the case is exhaustive, whereas before, because of approximations we took for outer bounded variable types, it was not exhaustive. This is a principled fix and it works for other expressions other than if expressions. Well, it was not worth it. The type system got substantially more complex and the exhaustiveness mechanism itself had to change, because now it had to reason about non-local variables too, all of a sudden. Then we measured over 6 projects, 27,000 functions, plus the student corpus. Outside of if expressions, not a single checking outcome changed. At that point, we wondered if we could target these if expressions directly. And we could. So we shipped a specific simpler fix instead. Collect every variable mentioned in the guards, put those variables in the scrutiny, rewrite the patterns with fresh variables bound to them. Now the scrutiny carries x, and with the spec, the guard refinement we already had narrows x1 to the non-negatives in one clause and the negatives in the other. The union is all of integer and the case is accepted. Without a spec, x is dynamic and dynamics waives the application anyway, so the rewrite helps annotated code just the same. 3 steps, purely syntactic rewrite, no change to the type system at all, and 43 false positives disappeared. For completeness sake, here's the rewrite as we defined it in the paper. The input shape is the desugared if, a case over the empty tuple whose clauses are wildcards with guards. The output is a case over the tuple of all outer variables in the guards mention, so that's x bar, and every clause rebinds them as a tuple of fresh variables, that's y bar, substituted into the guard and the body. On anything else, the rewrite is the identity. 3 properties. It preserves meaning. The wildcards bind nothing, so every x is in scope at the case. The fresh tuple pattern is irrefutable, so each clause fires under exactly the same condition as before. And single assignment makes the substitution sound. It is always applicable. It needs no type information, so it fires with or without a type spec. And it has one positive side effect. Take this function. X is an atom by its spec, and the if compares it to 0. Before the rewrite, the guard talks about an outer variable, the checker has nothing to compare it against, and the clause is simply accepted. After the rewrite, X sits in the scrutiny with type atom. No atom equals 0, so the first clause is detectably that, and the redundancy check now reports it. The rewrite tightens redundancy as well, not only exhaustiveness. We deliberately do not gate on it on any side condition. If the analysis can detect that clause, it should. One question is still open though. Why did evaluating an expert code never hit this? That's a pure population effect. Case outnumbers if 14 to 1 in production, and experts almost always end an if with a catch-all we already accept. That's mostly true. And students invert both factors. And if is, let's say, contested in the community. Roughly speaking, ending with catch-all true clause is idiomatic, and we already spotted that, but the non-idiomatic versions we did not. But being non-idiomatic is not a reason to reject it. That's the point of the study. If you only ever evaluate on an expert code, you will not find this class of problems, because it is very likely not there. A fair question at this point. Would any other checker have rejected this shape? No, and for a simple reason. Dialyzer success typing never report a missing case, and equalizer does not check exhaustiveness at all, by design, citing let it crash. So the rejection is the price of the guarantee. Only checker that verifies exhaustiveness can get this wrong, and the fix is to verify the partition, not to stop checking. And concretely, why not just lint for the missing true clause and tell students to write idiomatic Erlang? Because the community itself is split. Robert Werding has written that if was added hastily and that pattern matching makes it largely unnecessary. The NACA guidelines say, don't use if. Case over if has been standing advice on Erlang questions for decades anyway. But the explicit partition has principal defenders on the same list. Mildly annoying when writing the code, enormously helpful when reading it, and the well laid out if reads like a decision table. A lint picks a side, but verifying the partition serves both camps, I think. So the 3 questions on student code. Fast enough? Yes, in our opinion. Invasive? Not too much, and 1.5% of exhaustion checks would need an opt-out. False positives? About 5% of checker reports, that's 0.5% of functions, and between 75 and 95% of what we report is actionable, depending on how we let it crash. What we got out of this are 3 formal refinements that we're not going to use. You can look at them in the paper if you want. And instead, a much simpler syntactic rewrite that covers every important use case. And next up, exorcism maybe as a second corpus to test against, maybe a catalog of rookie mistakes, and actually measuring whether any of this helps people learn. That's our main goal. We've not put the checker in front of a class yet. That's the next study. If you teach Erlang and would like to try a statically typed version of it in your own classroom, that's our Matrix channel. We would gladly help to set up your course with the checker included. Feel free to reach out to us. And that's static types for Erlang. If you want to try out the online playground where you can try Analyzer in your browser without installing anything, there's the QR code. Both Erlang and Elixir, with some caveats, are supported. The open source repositories are bottom left and Matrix channel is bottom right. Thank you, and I'm happy to welcome you to our Matrix channel.
Thank you. Thank you. So he's gone, right? All right. Okay, yeah, and I can see that, yeah, they're on Discord. If you have some questions, you can hand them out to him. Send them to him. All right, our next presentation is ready to start, hopefully. This would be Gregory Morse. Let's see, let me get to the right spot here. Gregory Morse is a PhD candidate and lecturer at Eötvös Loránd University in Budapest. His research spans programming languages, concurrent systems, and decompilation, with his doctoral work focusing on incremental decompilation. Gregory will present towards exact semantic equivalence of Erlang beam constructs, lessons from advanced emulation and decomposition. Please welcome Gregory Morse.
Okay, thank you for the introduction. So yes, and my work here today about the semantic equivalence of Erlang beam constructs derived from some work I had done earlier that was supervised by Melinda Toth, who's my co-author here. And so let's get into it. Essentially, the idea was that we were doing a decompilation project before. And one of the things was looking into an intermediate representation-free way of just simply representing the Erlang beam immediately in pure Erlang abstract syntax tree form. So that's maybe an unusual approach to decompilation, but in Erlang, it actually had a relatively natural fit, and there was a lot of success through that. But it led to some observations, because one of the things that motivated was not just the decompilation itself, but it motivated writing an emulator in Erlang for beam code. And this is different because everybody knows about eval, right? And that's an interesting tool in its own right, but it doesn't actually compile to beam. It's not doing JIT. right? So it's actually direct AST emulation. It's a bit different. So this is kind of a special perspective where we're actually emulating Beam code. And so basically, the idea here is that can we actually look at this boundary and define the actual boundary of the behavior of what's representable in Erlang versus what Beam can do that is very hard to represent in pure Erlang? And can we kind of define a exact surface or frontier of where there's going to be semantic equivalence issues, okay? And this can actually potentially improve the language. There's going to be positives and negatives from this because, for example, maybe, for example, people would think that, okay, this actually is just going to help people with their decompilers because it actually simplifies things where you don't need an IR represent, you don't need an IR at all. You can just represent the language within its own constructs. But there's also the perspective that this can actually add quality and value to various refactoring and verification tools, et cetera, and so forth. It can make the eval library itself in Erlang potentially more efficient. So there's the standard three things that we're going to be looking at here are evaluation with the arrow eval function, which essentially just runs an abstract syntax tree in pure Erlang using the standard library. And then there's interpreting Beam code. And Beam is very easy to disassemble. And then you can just, instruction by instruction, go through it. And then there is the kind of the gold standard that I guess we assume that Erlang is, in the actual Beam VM. That's the actual behavior that's very efficient and optimized that we want to make sure we are actually matching. And so, okay. This kind of notion of semantic equivalence needs some agreement, some groundwork to lay exactly what we're talking about here. So the exact definition we're using here is basically, functional equivalence stuff with return values. Also, exception handling needs to be identical. The mailbox effects, this is, of course, going to be the biggest deal and one of the hardest, as well as the timeout behavior. So the special receive instruction is going to be key here. And as well as closure identity and callable behavior. Okay, so there's stuff that's like unreachable code, right? And we'll look at an example of that. And then there's things like, which kind of goes right up to what we just were saying with exception handling, stack traces and line metadata, because essentially this is part of the semantic information available to a program, and it can be checked, can be introspected, right? That could be a protection mechanism that you look and make sure the program hasn't been tampered with merely by doing something to create an exception and check the stack. So that's what we're talking about. And what we are not talking about is the exact wall clock timing, the implementation costs, and all these kind of things that are, they're kind of a separate discussion because they would require maybe deterministic hardware, a deterministic operating system, stuff that's kind of effectively considerably outside of practical control, okay? So we aren't analyzing those types of things about actual CPU and memory usage and such, okay? Because those would be very challenging to resolve. Okay, so here is the analysis from doing a full decompiler and learning the lessons of where the things are kind of mismatched, okay? And some are actually easy to potentially solve in the standard library if, and it was considered to be worth doing. So binary matching is going to be the first one we're going to look at. And that is because the binaries in Erlang are using a match context. And by doing this context, it breaks the pattern matches that we normally do into some micro ops. And because of that, well, those micro ops, they can be represented, but it's not very pretty to look at, the representation of the code that would actually implement that. And we'll take a look at that. Next is funds themselves, right? So the functions have this closure environment, right? And that's one thing that if you're capturing variables, you might be influencing things during your emulation. And the other thing is there's an arity limit. And this is a very interesting thing, and it's different in the actual compiled Beam code and the evaluator, which is a kind of a strange inconsistency. It seems very practically oriented. And then we're going to look at selective receive, because this one is probably one of the most important if we really wanted to actually have this kind of idea that a language's compiled code could be represented in the language itself. This would be one of the most interesting to solve by far, because selective receive creates some interesting problems. And then finally, we'll talk about the stack data as well, and where that leaves things. So so that's the boundary we're going to look at. So just some examples here. So if we look on the left side here, this is going to be an example about binding. We have a function that takes two input variables, and it's doing something where it's setting a variable r to 0 or 1, depending on if a or b is true. And then it kind of catch-all emits an error, and then it emits r. Now, that is not allowed in either the Erlang evaluator or in the compiled Beam code, right? That's going to cause an error, a compiler error, or an evaluator error. And yet, if we have pure Beam code, we can represent sort of things like this. We can have an error, and then we can have some unreachable code. And so it becomes a question, well, you know what I'm saying? This is just a simple representation question. So these are the kind of things we are thinking about. I'm not saying this is a particularly important case. It's just grounding the perspective, okay? That you can have stuff like this in Beam code that in Erlang code you obviously couldn't have. Okay, next, the metadata. So this is also something that's first off, you're able to maybe modify the Beam code so that it has, not data that's come from a true compile. It's been, tampered with, and they're optional too. You can actually clean that out and not have it. So that does change the semantics of when you're emulating it or, trying to decompile it. So those are the kind of just small examples before we go into this. So the first major case, binary matching. And this one is definitely the most straightforward. Basically, there's going to be some decoded values while you're doing this matching. And the match context is basically doing some checks with some predicates and some getting type functions, okay? And this specifically is talking about floating point numbers, UTF encodings, and non-aligned bit fields, okay? So this is where this one goes. And here is such a predicate, okay? So UTF-8, and these ones are really kind of, you somehow wish, and you can look in the standard library, there's just, somehow it would be nice if Erlang had these functions kind of built in, maybe, right? Of course, we can implement a bunch of code to, implement the official standard on what is a UTF-8 or not. But I didn't show you the code. It's in the repository. I will link later. But it is long and ugly, boring bit checks, right? So just a lot of different tests for 1 byte, 2 byte, 4 byte, all that. So basically, the matching system has Beam opcodes. I'm not actually showing Beam code in this presentation because I want to keep it more looking at it from the Erlang perspective. Okay, but there is a Beam opcode for these types of functions in the matching system. And so the has function will be checked, right, to check, does it have this? And then the getting function will actually get it there's a match, right? So these are kind of two really case in point examples of what is hard to emulate in Beam code. I mean, you could put a big blob of code to do it, but it's the question, why not just have these in the standard library? Maybe with custom Beam code that just somehow reuses that matching system. Or even, I would even propose that the opcodes that do the matching actually, maybe there should be some more general opcodes that can be used inside and outside of a matching context. Because these are just nice utility functions. That's all they are, right? So, so here's the list of what we're talking about here. The float, the UTF-8, 16, 32, and the stuff for the bit string, the bit strings and whatnot. Yeah, so that's get integer, get bits, and skip bits down. So those are the actual opcodes in the Beam code. And it's just a question of why don't we have some other way of accessing these without emitting some really nasty code? Okay, so this by far the easiest to fix. This can be pretty simply expanded into the Erlang standard library one way or another. Might raise some questions again about opcode reuse, considering the matching context requires a context, and these are kind of more raw tools. So, okay, number 2, the fun adapter. Okay, so this is an interesting one where if you're trying to emulate and you want to do a perfect job, you're going to eventually hit, okay, the language has a syntax limit of 155, right? But okay, 254 is okay, because the problem is when you're emulating, you need to capture one variable, and that hits you to 255. And that's the one thing, the arity is also tied up with the amount of capture variables. So captures counts, right? And so what happens at 255 is you can't emulate it. And then you're kind of scratching your head how to do it. Well, it turns out, and here's the example on the screen, that if you used a named fun, you can have the 255 arguments not capture anything, and you can do this clever little erasure scheme, and then you can put the new fun onto fun. You can do some tricks here, okay? This is some really strange little tricks to, avoid the closure issue where you're actually tying up the arity. So this was the best I could come up with. But as we can see, this isn't really a nice or smooth thing. We know languages like Java have used var args, and many languages have tried to use var args as a way to kind of like maybe avoid these kind of bounded number of inputs on functions. So yeah, so basically the erase named fun, this is kind of the key little point there, that when you do that, the closure maintains its immutability. And yeah, it avoids this 255 arity limit and allows you to actually still emulate a 255 variable function. But yeah, it's a little bit, it's got this limitation that it's one shot. Of course, that one shot is not a real serious limitation. That's more of a caller issue to deal with that, right? It just needs to know about that because it's using this put function. And then, yeah, basically, it would be nice to have better reusable adapters so that we don't have weird boundary cases, right? So this is one of those boundary cases. Somehow or another, maybe var args is an option here where it just uses a list or something, or a tuple, right? Somehow, because that's actually what we're using here is a tuple, right? But at the end of the day, there's probably should be some cleaner generalization at this boundary to make it easier to emulate. And interestingly enough, and this is it kind of goes into the details, the eval function in Erlang only accepts up to arity 20. Okay, so they thought, I guess, practically who's going to call a function more than 20 variables, put it in tuples, put it in some other structure, and get those arguments down. So in fact, I would recommend nobody ever uses more than 20, just because you might want to eval some of your code, and then you'll all of a sudden have to refactor because, so there's certain practicality to all this, but this is an interesting mismatch that the eval has to actually spell out one by one each single function of different sizes, right? And they just kind of didn't want to spell out 255 of those and then deal with the boundary case that I dealt with, as I showed you through the other method. So yeah, so there is this strange mismatch in behavior due to this. So, okay, that's number 2. Now we're going to go into number 3, which is the selective receive. And selective receive is this kind of issue. And by the way, Erlang eval definitely has to implement this one, and I do something relatively similar to what they're doing. So you're going to have to scan the mailbox without losing messages, and then you have to find the exact match so that you can use it. And you still need to deal with all the suspending and waking up behavior, because you don't want to go into some kind of infinite polling or whatnot. You need to ultimately have the timeout still being respected and being processed correctly. And yeah, so this is one of the hardest surfaces in the language to truly say that you're exactly emulating it properly. The approximation that I came up with, because I wanted to just have something, again, that could be used in a decompiler, just to, a clean piece of functional code that you could just drop in. Maybe you can pattern match this out later. It was kind of the idea is use some pattern matching to clean up the code eventually. But this is really, it's a bit sketchy to say that this is really equivalent, right? Here we've got the actual function that's doing the receive here. So we've got this message classifier, right? And then we basically are checking if we got the match, and otherwise we go back into the receive loop, and we have to keep track of a message queue ourselves. And this is exactly what Erlang eval is, something very similar to this. And we have to check these times, right, to see if we've exhausted the total time from the start, right? So we have to keep polling the time every time a message is received, add to the message queue, and then we have to have more wrappers. This is kind of the internal function. This is the primitive. I'm not showing you all the code involved in actually doing this. I'm showing you the key place where we hit that semantic boundary and mismatch, and that we have to try to resolve using something like this. So this would be one of the biggest improvements, would be something where you could actually have some special selective receive function. Probably would be one way to do this instead of just the normal receive, that you could have a but it raises a lot of questions to think, can you have a receive that is somehow got a conditional function like this, so that we can support this more dynamically? So that's a real challenge for how to actually cleanly implement this. But it would also improve the eval functionality, right? Which definitely performance-wise is not going to be anywhere near as efficient. So there is a serious efficiency issue with trying to emulate it using such a style, right? So even computational complexity wise, right? Keeping those lists. So, okay, the last case. The last case is the stack trace. So the beam actually is also storing line numbers. It'll have like these little line number kind of opcodes. You just have to kind of keep track of them. And so one very important thing is that if you are writing an emulator, you do need to keep track of those things if you want to deal with especially with a program that is introspective of its stack traces. That's again, part of the semantic landscape of the program, potentially. And so the other thing to compare this to AST evaluation is interesting that the Erlang eval is actually giving you the wrong stack trace. So Erlang eval, if something goes wrong, you're going to see its own stack trace. You're not going to see the stack trace of the code that you sent to the eval function. So it's not actually emulating the source program frames in the way that you might expect it would. And in fact, an eval function may be more useful if it did emulate the source program frames and not have its own emulator apparatus in the stack traces. Okay, so there definitely is a equivalence difference if you do use the eval function. Of course, when we emulate it, we don't, we're doing things from the Beam perspective at that point, so we don't need to run into that limitation. So you basically have to maintain this emulated stack, including the module function arity and y. Okay.
Gregory?
So this
Gregory.
work has been published, and there's also a code supplement that we provide that you can find on GitHub. And the primary scripts for the semantic equivalence part, because I don't want to, there's the rest of the stuff with the emulator and the decompiler, it's all there as well. But the main scripts are this semantic equivalence script and an extra supplement that has more test coverage and the validation. Okay, so the executable validation all passes. Like, I've tested all of this. This is all pretty well proven, at least empirically. Okay, and even validated a large amount of state space on some of the UTF helpers and all this to make sure this is actually correct. These things are in the paper. You can see kind of how ugly they are, but that currently is probably the most direct way of doing things. I suppose you could do some custom Beam code stuff to try to do this as well, but that runs into its own issues. So it wasn't really the right approach when you're trying to represent Beam in Erlang to then try to re-represent it in Beam with some compile, just-in-time compile. That doesn't, you know what I mean? It's a mismatch of the intent. So yeah, and all the arity stuff is there, and you can see all these discrepancies as well as the receive functions.
Gregory?
The boundary, just to summarize it, binaries, yeah, we can do that pretty nicely. Fun wrappers, mostly, there's some like little details, especially at the 255, and again, the Errol eval also having its own limitations. Selective receive, this is really a pretty rough approximation, and it would be really interesting to see a resolution to that. And yeah, the stack metadata, it can be done, but the host evaluator is not really doing that in the same way that one might expect. It might be more useful. So yeah, that's kind of this boundary frontier. And to me, what's exciting about this, okay, what is exciting here is that nobody thinks like this and no languages do this. So to me, it would be really fascinating to see a programming language actually achieve this and say that they've been able to achieve something that is, at least from a theoretical standpoint, perhaps interesting, okay, to have this ability to perfectly emulate all your compiled code language, right? So, okay, takeaways here, both basically covered them. So the compiled Beam is going to be the kind of, as I said, the gold standard before. That's the kind of behavior that we all are going to primarily trust. So we are trying to basically get these other methods to model that. And we notice a few discrepancies, and they raise some questions. They raise some are language design questions. Some are maybe more like the binary stuff, more just kind of, okay, these could be implemented. They're not really serious. They're small design questions. Some are big ones, like the selective receive. And yeah, the gaps are going to be hidden state stuff, whatever, a context, right, we're going to look at. And so, yeah, that's basically it. Thank you very much for letting me share this with you.
Thank you. All right. Questions? We don't have any that are posted. No face-to-face questions. Great. Okay. Thank you. Thank you very much.
Yeah, I could ask a question. Yeah, I'm just curious, do you have any thoughts on how you might handle the hidden state in the future? You think there's a way that we could add type annotations to talk about that or something?
Yeah, I mean, annotations are definitely that's definitely one valid technique. And I, honestly, that's one thing I was thinking too is when you have when you're representing your, for example, decompiled Erlang as an abstract syntax tree, you could always have some special decompiler annotation that just handles some of these hidden state issues right up front, and you still don't need an IR, right, to deal with that. But yeah, that's definitely one possibility. For the binaries, I think we need another standard library and probably a little bit of beam tweaks to, you know what I mean, to maybe share opcodes a little better with the matching stuff. And I don't. The selective receive is it's a tricky one that I don't want to necessarily push something that uh, has some other restrictions, right? Because that one transcends the whole VM in a sense, and some of the language design. So yeah, that's my thought, at least for some of the specific ones. But yeah, hidden state in general, I agree with you that annotations are probably uh, maybe just a safe out until you have a time to deal with these things, maybe at a language level. So I definitely like that idea.
Yeah, I always worry about how hard it is to write and maintain these annotations, but we're living in the future. 2026, we've got LLMs to make a good guess.
Exactly. Yeah, and that actually, this is a great point. That changes the maintainability of certain things like that, right?
Okay. Anything else? I don't want to. I jumped a little too soon. No? Okay. All right. Thank you, Gregory.
Thank you very much.
and get started.
Let me know.
Okay. Where'd we go? Disappeared. All right, our next speaker is Daniel Ferenczi from Eötvös University in Budapest. Daniel and his colleagues have been exploring how Erlang's messaging and monitoring capabilities can be extended to low-power and long-range wireless environments. He'll present EML, Erlang messaging and monitoring over LoRa. Please welcome Daniel Ferenczi.
Thank you. Hello, everyone. My name is Daniel Ferenczi. I'm a PhD student at Eötvös University, Budapest. Together with my supervisor, Melinda Tóth, and Gergely Ruda, an industrial expert at our company, we have been working on an Erlang library for node monitoring and remote messaging over LoRa communication. In this talk, we will discuss what led us to develop a library for messaging and monitoring with LoRa. We'll show the requirements we defined for our library and discuss some technical details of how it does messaging, monitoring, and show its limitations. Back in late 2025, we were interested in developing a microcontroller software in Erlang for nodes that communicate over the LoRa radio communication technology. At OnVM, a bean runtime scaled for low-powered microcontrollers in the range of the ESP32 or STM32 supports building applications for embedded devices. The driver is also available for using an on-device LoRa modem for communication. LoRa is a low-powered communication technology capable of sending small frames of data over large distances spanning multiple kilometers. LoRa is popular for IoT use cases where devices are deployed remotely and only transmit small amounts of data. We were interested in building a prototype for a leader election system using AtomVM and LoRa. We chose Garcia Molina's Bali and its fault-tolerant version, the invitation algorithm for our work, as we found them simple to implement. Bali is a simple leader election algorithm where cluster members select the node with the highest identifier as leader. It assumes reliable networking and that nodes do not pose. Invitation algorithm relaxes these assumptions and accounts for network partitions as well. In the event of a network partition, the nodes that can reach each other re-elect a leader among themselves. If the partitions merge again, a new election process takes place, but a new leader is elected for the merged partition. Partition tolerance is important for LoRa-based systems as messages sent over this radio communication technology can get corrupted or fail to reach their destination. Our high-level plan was to get familiar with the algorithm and test our concept with a version running on standard Beam nodes on our workstation. By running it in a controlled software environment, we could easily stop and restart nodes to validate if leaders are elected and replaced as specified by the algorithm. Invitation algorithm was harder to validate, as nodes are expected to tolerate and recover from network partitions. To validate the system, we placed our Erlang nodes in containers and simulated network problems by changing their networking configuration. This was convenient enough, as we could find and fix implementation bugs quickly. Our implementation builds on Erlang's actor model, specifically distributed Erlang's internode messaging and monitoring. As a consequence, porting to AtomVM and LoRa was more challenging. Our AtomVM nodes only communicate over AtomVM's LoRa driver. The driver implements simple protocol for communication, but is different from Erlang's interface for sending messages. We could have adapted our leader election algorithm to the communication functions of the LoRa driver, but this would have had to repeat the validation of our leader election algorithm. We wanted to avoid it as much as we could. It would have meant reevaluating the algorithm on actual devices. For this, we would have had to deploy them to actual devices, as the 3 devices on this picture. But validating the algorithm, especially its fault tolerance, would have meant triggering actual errors instead of simulating them. For example, we could handle device failures by disconnecting or restarting the actual microcontrollers. Testing partition tolerance, however, was particularly inconvenient. On this picture, we have shielded our devices in 2 groups by wrapping their LoRa antennas in tinfoil. For example, in these pictures, I've split our original setup into 2 groups. On the last picture, you can see a single device with its antenna shielded. On the right picture, the 2 devices have their antennas wrapped together so that they can communicate among themselves. After removing the wraps, we expect all the devices to elect a common leader among themselves. And in the meanwhile, we monitor the devices and their logs to see if the system behaved as intended. While eventually this is a necessary task for validating the system, ideally we want to perform it as seldom as possible. At this stage, we looked at what we had. A working leader election algorithm for beam nodes that relies on Erlang's internode messaging and monitoring. Ideally, a port should not change the leader election implementation and should only affect the underlying communication. For example, if the LoRa driver's messaging were extended to work similarly to Erlang's actor model, we could simplify porting our system. As LoRa is a physical level wireless communication technology, the AtomVM LoRa driver's most basic communication method is a broadcast function. The driver implements a simple protocol on top of it that lets programmers configure a name for their devices and send targeted asynchronous and synchronous messages. Users of these functions still need to take transmission times into account, as initiating new transmissions before finishing the previous one results in lost or corrupted messages. Programmers must also wait between transmissions to comply to regulations. For example, the European Regulatory Standards Institute defines idle intervals the sender must wait before sending new messages. These intervals depend on the time spent transmitting and can be calculated by knowing the size of transmitted messages and the configuration of the LoRa driver. Our goal was to build a library that offers LoRa-based messaging and monitoring, building on top of LoRa driver, and handles data specific to LoRa. With these details in mind, we defined the requirements for our library. First, it should provide a similar interface to Erlang's messagings to simplify transitioning existing Erlang applications, like our leader election application. Then message senders and recipients should not be aware of any overhead email ads to messages. And lastly, failure notifications should be regular Erlang messages, just as notifications from failed Erlang nodes. We want LoRa-based messaging to have an Erlang-like interface with any details about previously initiated transmissions and handling regulatory compliance hidden from our application's logic. This defines the library's interface on both the sending and receiving end. Email hides the details specific to LoRa. On the sender side, it queues transmitted messages until current transmissions end, avoiding message loss by interrupted transmissions and ensuring regulatory compliance. This functionality is provided by parallel gen servers handling the queue and invoking the LoRa driver's asynchronous send function on POPed items. They also construct the payload of the sent LoRa frame, including the reference to the target process. On the receiving end, email unwraps the received payload and sends the contained message as a local Erlang message to the target process. Email wraps the AtomVM LoRa driver for both sending and receiving messages. It uses the driver's thin protocol for defining node names and using them for asynchronous messaging. In fact, it expects clients to use these node names when they specify the destination for sending a message. Altogether, we use Erlang's interface for email's messaging so that applications can be ported more easily. In the case of monitoring, we do not have something analogous to an EPMD server, and our devices do not have connections either that we could monitor. To define a path, we looked at the roles nodes can have in a monitoring relationship, a monitored node and possibly multiple monitoring nodes. Email expects a healthy monitored node to send messages to nodes that monitor it at regular intervals. This definition can be improved, for example, by taking into account any recipient a monitored node sends a message. For now, email monitoring nodes only take into account messages sent to them. Email also defines a configurable activity threshold. LoRa activity of nodes within range is tracked continuously by email. A concurrent process checks if any monitored node has been inactive for longer than the configured threshold. In this event, it sends a node down message to the process that set up monitoring. It may occur that a monitored node fails, recovers, and resumes transmissions within the threshold. Distributed Erlang detects such quickly resolved transient failures, and we also want to handle them with email. To detect them, nodes add their onboard monotonic time in the message payload. This timestamp measures the time elapsed since the system started. Email's monitoring feature tracks the timestamp of the last received message per node. If the recorded timestamp is higher than the message it has received, then we assume that the monitored node restarted and report it as a failure. Monitoring is set up with the email monitor function. It takes as arguments the node's identifier and the Boolean flag to turn monitoring on or off for the specified node. The spec of its interface functions is also identical, making porting applications simpler. To work with email, a developer has to initialize its background services as done on line 1, which also takes care of initializing the AtomVM LoRa driver. Afterwards, sending is presented in line 2, and the setup of monitoring in line 3. The receive block starting at line 4 is expecting the note down message for the monitoring we have just set up. Among EMO's limitations, we want to highlight that it offers no authenticity or encryption for messages. The AtomVM API contains the necessary functions to implement HMAC, for example, but working on this would increase the message payload and consequently the transmission time in battery use. At this moment, EMO adds about 45 bytes of data to the original payload of sent messages, which is further increased by the node's name size. Compression options are under development for AtomVM, and once released, they could offer options for optimizing transmission sizes. Monitoring can also be improved with a new definition for healthy nodes. By taking into account any messages sent by monitored nodes, scenarios where multiple nodes monitor the same device can be built with a lower message flow. Developers also have to take into account the reliability of LoRa communication. Monitoring is especially sensitive to this, as if a monitor node has its messages corrupted, it will eventually show as unhealthy. Out of these limitations, we are especially looking at improving the definition of healthy nodes and EMO's security in our future work. We are also working on implementing code checkers and refactoring rules that help automate the refactoring of a regular distributed application to EMO with the refactorer code transformer tool. Finally, we are interested in building a verified leader election algorithm with Erlang and look at what changes are necessary for it to work with EMO and run on microcontrollers. We would like to conclude our presentation by listing the changes we had to do when porting our algorithm from Beam to AtomVM. Apart from changing the module names for messaging and monitoring, we only had to adapt how we do random number generation and ensure that EMOL and ESP32 specific application parts are only used in our microcontroller builds. Also, as messaging on Beam does not need to stay idle after transmissions, we could readjust some timeouts and idle times so that we could test our algorithm faster when we did run it on our workstation. With that, I would thank you for your attention, and I'm happy to answer any questions.
Thank you, thank you. We don't have any online questions. What questions do we have in person? Okay. All right. Thank you very much. That was great.
Thank you.
Let's move on to our next presenter. Okay, I've got to get to the right spot here. Well, 10 minutes early, so we'll take a little break. Wouldn't want to get ahead of schedule. Might mess up people joining in. So, all right, good. Let's do that. Our next speaker is Yusuf Garbi from Eötvös Loránd University in Budapest. His work with Istvan Borzó and Melinda Toth examines an increasingly important question for programming language implementations. How can we meaningfully represent not just performance, but energy use? Yusuf will present green benchmarking in Beam languages. Please welcome Yusuf Garbi.
Thank you. Today I will present the energy consumption of the Beam languages, also with the performance. The main languages that we are studying are Erlang, Elixir, and Gleam. Before I start with the energy consumption, I would like to say where the green computing in our paper sits. It's if we look at the green computer,
Yusuf?
Yes.
We're having an audio problem. You're tending to be very muted. We can hear you, but just barely. Is there a way to be closer to a mic or something? Could you be closer to a mic so that we can hear you more clearly?
Can you hear me now?
I can hear you right now. It was, we could hear you and then we couldn't, and then we could hear you.
Okay. Is it fine if I start all over?
Yeah.
Okay. Thank you. Good evening. My name is Yusuf Garbi, and this is a joint work with Istvan Borzó and Melinda Toth. Today I would like to present to you the energy consumption of Beam languages, also with the performance. So before we start with the energy consumption, I would like to talk about the green computing and where our work is sitting in the green computing field. So we have basically three levels. The first, which is the hardware, and where we are trying to build efficient processors and design better chips and better cooling. The next, which is the data centers, where we try to try to use virtualization, basically moving workloads into some or less hardware or physical machines. And we also have the possibility to join or to place our servers into closer geolocalizations in order to have less energy when we transmit the data. And we also try to use cleaner energy, so basically using solar or wind energy. And the third, which is software, and this is where our work sits. So where also developers and engineers, when they write code, they actually basically have the most control of it. With the rising demand on the cloud services, edge computing, machine learning, we have our work sitting at the third level, which is the software level. Basically, this work was not a recent one. So we started the green computing at ELTE a few years ago, and our first was the language construct. So we studied the language constructs of Erlang, the energy consumption of Erlang on its own, and then we moved to comparing Erlang with other programming languages. And then we also studied the energy consumption of distributed systems such as Akka. And then we moved to the web servers, basically where we are, at this stage, we are building a framework that allows us to measure the energy consumption, the performance of the web servers. And we also measure the energy consumption of Erlang compared to other non-Beam servers such as Nginx, Apache, and that sets the baseline for our own work. So the fifth step right now is to study the Beam languages on its own. And basically, we have a fixed runtime, and we are widening the language scope. So, and why energy? So basically, in the benchmarking field, energy is, especially for web servers, is less pronounced. So all of the benchmarks still centers on the speed, throughput, and they pay less attention to the energy consumption. But it's actually the gap that we are trying to fill, and basically we are trying to study the let's say the correlation between throughput, latency, and also the energy consumption. And we have, as we said, 3 languages. So Erlang, it's known for concurrency, isolation, and fault tolerance. We are serving Erlang through row socket handlers, but also through Cowboy and Yos. We have also the second programming languages, which is Elixir. So it's basically running on the same runtime, but used a bit differently. And we are also serving it through row socket handlers, but also with Phoenix, Cowboy, and Bandit. And we have Gleam, which is a relatively new programming language, and we are serving it through Mist. So here we have 1 runtime, but 3 different languages. So the comparison is controlled. And the whole research question is energy driven by the language or by the stack that we put on top of it? And so for this, we are basically at the stage of the framework. So we built a framework for this, and its main targets are the Docker files. So we pick a Docker file, we build it, we run it, and we run the workloads on that Docker file. We have different loads of levels of loads. We have configurable client counts, sizes of the messages, rates, durations, and all of these are preset, but it's also configurable. We have also up until this moment 3 families of benchmarks. So we have the static, the dynamic, and the WebSocket, and they all share the same pipeline and the same export format. So it's a CSV format, and basically the Docker image name is the single identifier for by default for the whole benchmark. So we try to trace back all of the results to that Docker container, because we are dealing with, in our case, 27 different Docker containers. So it's important to trace back the energy consumption to the Docker file. And basically, we are adding the folder selection and the new families in the future. And for the pipeline itself, so basically we start the target, which is the Docker file. We check whether it's responding. So we do a health check. We start the telemetry. We apply the workload, and we write the results. And we make sure that we, before each run, that we only have 1 active target. And we set some configurations like the high file descriptor limit, the standardized port mapping, but it's also possible to change the ports depending on the Docker itself. So it's also configurable. And as we said, we have dedicated health checks for each protocol. And we also have we are also using Scaphander to get the energy consumption of the Docker containers. And it gets the energy in joules, and for each active container, so it's making the energy energy measurement easier for us. And for each row, we get the container name and the workload type and the client settings, all along with the other metrics. And for the experiment, in our case, it's a modest one. So we have a ThinkPad X13 Gen 1. We have a processor, i7 processor, 10th generation. We have 32 gigs of memory and Debian 13. And for each run, we record the successes, the failure, the throughput, the execution time, the total and average energy consumption, processor and memory usage. And in our case, for the HTTP, we have 13 load levels. So we have 100 up to 80,000 requests. So each request is a client sending a request to the server. And all of these are driven by the by 100 parallel client workers, but it's also configurable, so you can set it up to your CPU or to your machine. For the workload families, we have the first family, which is the static HTTP, and we have two subfamilies. So the first, which is the called index, and we serve an index file from the disk. And the second one, which is trying to build send the HTML file through the code itself, and we call that pure. And we have 11 targets for those. Same thing for the dynamic, but here we are adding a small footprint of the dynamic nature of the server. So we just read the time of the machine, and we send it back in an HTML file as well. And we have the WebSockets. We have 4 subfamilies of WebSockets. The burst, which is sudden spikes. We have the stream, which we try to send a stream of sustained rate. We have the concurrency, and that's the basically having a small payload and a huge number of concurrent connections. And we have the payload, which is the basically a set of frames that grow gradually. And we have 5 targets for those WebSockets. And here at the bottom, we can see the different combination of the web servers and the targets that we have. We have Erlang, Elixir, the Pure, Index, Cowboy, Yoast, Phoenix, Bandit, Mist, and Mist for the WebSocket as well. And before we go to the results, first, all of the results are generated using this framework. So on the left part of the screen, we can see the data browser and live canvas. So we can import different CSVs. We can import folders, and it automatically gets the measurement or the type of the benchmark. So we select the benchmark type, we select the metric itself, and then we select the plot, and we can visualize and interact with the plot itself. And we also have the Export Studio on the right part of the screen, and basically that's making the exportation of different or of a huge number of graphs easier for us. So it's basically exporting all of the graphs for this paper and for all of other papers that we are writing. We can set the resolution of the image, the type, or the whether it's a PNG, a PDF, and so on. And we also did not include all of the graphs according to the limitation of the number of pages in the paper, but anyone can go into the GitHub and also generate the different or others graphs that we did not include. And for the results, here we have on the right side, which is the total energy in joules. And in the left side, we have the successful requests. and on the energy consumption, we can see that up until 30,000 total requests, there is not much difference between the graphs. But after 30,000 requests, we can see that there are two different bands. So there is the lower band, which is the row socket handlers, so which is either the index or the pure. And we have the higher band, which is the frameworks. And on the right side, which is the successful requests, we also see that around 30,000 requests, there is a point where the server starts to separate, and that's also for the straight line. It's for the row socket handlers, and the degradation happens on the framework. So all of the frameworks degrade at the same point, and also for the execution time and for the throughput. So at 80,000 requests, we see that Elixir Pure and Index both finish the fastest, so around 64 to 66 seconds, and followed by the Erlang Pure and the Erlang Index. And that's the first part of the cluster, but there is the second part, which is also the same thing. So the frameworks clusters, and we have for the throughput, we have the highest, which is Elixir Pure, followed by Elixir Index and Erlang Pure, and we also have the lowest throughput related to the framework clusters. So basically, the execution time scales gently up until 30,000 requests, and then it bends. That means that the servers that are doing delivering the most successful requests are using less energy and finishing faster. Same thing for the dynamic ones. So as we said, we have the dynamic ones. We added the small time into the HTML file, and that adds approximately 10 to 40 joules. But that's the cost of the dynamic nature, and we can see that we have the same 30,000 points, 30,000 total requests. That's the point where both clusters are created, and we have the lower band, which is the pure or the row socket handlers, and we have the higher band, which is the frameworks. Same thing for the successful requests. And for the WebSockets, we have YOS in the blue. So on the right side, it's the energy consumption. Left side, again, it's the successful messages. So YOS is in the blue, Bandit in orange, Erlang Cowboy is in green, Elixir Cowboy is in red, and the Mist is in purple. And we can focus on the purple and on the green. So at 100 clients, Erlang Cowboy delivered full messages, so 300 messages, and used 102, so approximately 100 joules, while Mist spent 1,119 joules and delivered 27 messages. But that's not the full picture for Mist. So to be fair, for the concurrency, we have Mist also delivering 15,000 messages. So in the right part, we have the Erlang Cowboy, Elixir Cowboy, and Elixir Bandit using the least amount of energy, followed by Erlang YOS and Gleam Mist. But these messages are so small, and on the right side, we have basically for 100 clients, when we have a higher frame, we have Mist, Gleam Mist, basically failing and delivering only 9 messages out of 100. So what we can see is that Gleam is successful when it comes to concurrency, but it's failing when it comes to higher frames. And basically, this is the separation from the connection compared to the payload. And basically, what we can see from these workload families is that for the static, we have two regimes. So the raw socket handlers and those that stay low on energy and complete the work. For the dynamic, it's the same pattern, but a little bit higher cost. And for the WebSockets, the ranking inverse. So we have the cowboy leading once the frames grow larger. And we can say that servers that keep success high also keeps joules per delivered megabyte low. And we have to address limitations, some limitations. So the first, which is when we have high load in the HTTP, we can see that at some point there is a kind of a separation between the raw socket handlers and the framework ones. And we are investigating whether this is reflected by the server or by the measurement setup. And another limitation, which is the single laptop. So we are having the client and the server on the same machine. And we also would like to separate that in the future measurements. We also have one run, but it's not. We had different runs during the development, and the trends were consistent. So the clusters at 30,000 requests were consistent. So the trends are the same, but we are trying to also build or improve the framework to be able to have different runs. And we also should say that Cowboy Bandit use were set to 64 megabytes frames, and in some cases a bit more. But for Mist, we basically Mist do not expose such options. So hopefully in the future, we will be able to have that in the API and to set a higher frame for Mist and maybe have a different results. And for a conclusion, the framework architecture mattered more than the language syntax in every family we measured, but it's not universal prescription because frameworks also give routing, middleware, and security, which was not measured in our case. And for the future work, we also, as we said, planning to create or use the connection reuse, and that might solve the issue of 30,000, the 30,000 requests, so the breakpoint. And we also would like to match the WebSocket frame limits. We also plan to have repeated runs and confidence interval and also some statistics. We also would like to introduce the cooldowns between each runs and having the client and the server on separate machines. And basically, this work is available in GitHub. And not only this work, but other benchmarks, other tooling, and feel free to use the framework and test it, either rerun the benchmarks or test it against your own machines or against your own web servers, and let us know what you find. And thank you. And welcome for the questions if you have.
Thank you. We don't have any online questions from the audience that's here. Thank you. We don't have any online questions from.
I mean, there's one here as well, right? I'm interested in, did you look into why Gleam was so far behind Elixir and Erlang in the measurement?
So you mean in the WebSockets part or in the?
Yeah, in that one. Yeah.
Okay. So it was behind in some cases. So probably in the concurrency was not that behind because it also consumed 12 joules of energy and was able to deliver 15,000 client messages. Sorry. The only part where it misses is the higher frames. Same thing for the burst. So when the frame increases, Gleam seemed to fail. And that was probably because of the limitation when we try to set Gleam with Mist, configure it with a higher frames. We did not find that option in the API, so probably in the future we will be able to do it.
Thank you.
Thank you.
I have a question. So you mentioned at the beginning that you were benchmarking off of 2C web servers. Are they your zeros, or because I'm not seeing them in your graph anywhere?
C?
Yeah, I thought you mentioned that you were looking at Nginx and Apache as your baseline.
That was in a previous work, not
Oh,
in this
okay.
work.
Okay.
This work is dedicated for the Beam.
Okay.
Web servers.
So
Yeah.
you're not doing that cross comparison then?
Yeah, we did that in previous work.
Okay. Okay. Other questions? Okay. All right. Thank you. Thank you very much.
Thank you. Thank you.
And we have 2 minutes for our next one starts. So we'll just wait patiently.
Hello.
Yes. Yeah,
Yes.
we're waiting for just a minute, and then we'll go.
Okay.
ahead and
Okay.
start.
Just say me something to start.
Just let me know when we're on time. We can start now? Okay. Our next speaker is Sergey Starlo. Sorry about that. Starlo.
Sergey Staroletov.
Thank you.
Okay. Hello, everyone.
Sergey's research interests include model checking, formal verification, model-based testing, cyber physical systems, and systems software. Today, he brings those interests into the classroom with modern Erlang teaching, from code refactoring to actor system verification. Please welcome Sergey.
Thanks a lot for the introduction. Can you see my slides?
Yes.
Yes. Okay, fine. So I'm mostly a teacher, so I would like to present my research on teaching Erlang, because I'm teaching Erlang for more than 10 years. And so I would like to start from refactoring imperative code to comma-free functional code. I would like to discuss how to learn and teach recursion through mathematics. Also, I would like to present my experience using Java and Java interface with cooperation with Erlang nodes. Also, I love to teach how to spend a lot of processing time on a teeny server using lightweight processor. And also I developed my own consensus protocol model, and it model was created in Erlang. So I would like to share my teaching experience of real examples to my students. Also, I have a major part of my research connected with verification. I love to verify using Promela and Spin and other model checking tools. So I bring some my verification experience to the teaching of actor systems. Also, I will discuss my end-to-end laboratory approach. And also, we all think how to countermeasure with AI. So, because students love now use UI, and we should think how to deal with it. So I would present my recent ideas. So why Erlang we all know, and for me it is just one real world language, a usable language, because there are a lot of functional languages, but I think mostly none of them are used in production. I know only example of OCaml language, which is popular in France. So a lot of people use OCaml because it is functional and also imperative, because user can start writing imperative code and then refactor them to functional one. So in Erlang, we could do the same, I think. So what about my course? I spent a lot of teaching now, and I teach in our master's program software engineering at Poznań-Altai State Technical University, which is located in Siberia, Russia, in the heart of Russia. I think we have students with different backgrounds, and because we do master program, and some of them are going from our software engineering direction, but some of them are going from other directions. So we should teach them languages like first languages, C++, Java, and also in master's program we have strong parallel programming courses. So they start to write programs, and then they coming to me, and I would like to share my experience with teaching Erlang to them. So because in our, I think, region, there are a lot of companies and persons, the students do a lot of programming work, but functional language are not popular. So most of them start from imperative approach, and my way is to introduce some functional thing to them. And I am teaching vanilla Erlang because we have like course of presentations where students present their ideas on developing new languages, and in this presentation they present Elixir and Gleam languages, and I am concentrating in vanilla Erlang. And I love this citation. My student once said that Erlang feels like liberation after C code, after C sockets and mutexes. So we start how to refactor imperative code into functional code. And once I was in Microsoft Research School in Russia, because there was some good times where big companies invested in Russia, and you see those lectures in this school, and I love this slide by Satman Singh because he just presented crossed out semicolon, and that means that if we program good functional, good parallelized programs, we should avoid this comma. And you know all that in Erlang there are commas as statement separators, and you see, if we study some examples, for example, I start with example to process all files in a directory and to traverse the directory using recursion. And the first code that we present, and first code, this is understandable students, is just using variables and using commas, a lot of commas, and the recursion. So we should avoid to from these commas. Our goal is introduce like sequence of function calls, and we presented some refactoring methodology. I think there should be 5 steps. First, isolate side effects. Second is introduce intermediate functions. Then pass results as parameters. Other step is replace if with pattern matching, and finally eliminate code duplication. So our goal is this, and we have this imperative code. This is in the first step is understandable students. So we see that construction could be dedicated to a function. Then we replace sequential calls into just a call where we pass some functions that constructs parameters. Then we replace ifs with pattern matching. Then we combine calls of functions, but we see we have some duplications. So we insert some helper functions, and then we have just process one function in this example that has only one comma, and this comma is just a recursive call. So we received final comma-free code, and you see this only composition of functions, but we started from code. This code was quite understandable by students, and this code is functional, but also is understandable by students after some instructive training. So we have variables, if conditions, dependencies. This is hard to parallelize, and after the refactoring, we have just function composition without unnecessary variables, pattern matching, and so on. So now we are proceeding to approach of learning recursion to mathematics, because all of instructors study recursion using just factorial and Fibonacci functions, but it is enough. We need more sophisticated example, and also this should be understandable by students. So I proceed to Taylor series, and we understand how to compute each term from the previous one, and introduce this implementation in Erlang. and we have two accumulators computing recurrency factor, two termination criteria, and other things to by students to refactor and to reduce arguments imperative, for example. And we also can compute PI, exponential, and so on. And the main requirement is to use a unit test here because, we have PI function and we can calculate PI using series. So we could easily check this. And how to teach this incrementally? Start, of course, from factorial, then continue with Fibonacci, but we see some dramatic slowdown, and we now, after factor of Fibonacci, we say that there is no for loop in Erlang, so we should introduce for using recursion, and then we see how to receive next series from the previous one, which parameters we should need, next term, how to calculate, and we do it using group work, using only a projector and a laptop, and introduce students introduce their ideas, and we build the recursion of sine function or PI and so on with students in using increment way. So we should learn recursion by an increment way. Taylor series, this is a good example, and we should use incremental teaching. And of course, we should introduce a unit test and how to parallelize probably this code. Okay, then this is good. I think this is a good point to study Erlang when we interact it with different languages, and the best way is to make interaction with Java using Java interface library or G interface. So you could find this jar file. Why Java? Because Java is very popular, and a lot of students in our country or our region study Java and make some financial project with Java. So this is a good library because they use EPMD protocol for node discovery implemented in Java, and so we could interact with Erlang nodes by introducing pure Java nodes, but we should think how to pack and pack Erlang data types. So we start from creating Java nodes. They have some mailboxes available in Java code, and like you create OTP node, set cookie, and we could usually write a ping pong application in Java. And the main problem is how to send and receive something, because Java has types and Erlang has tuples with any types, easy convertible to other. And you see, in Java, we should cast the type. We introduce tuple and then create like new UTP Erlang object, new UTP Erlang atom, and pass PID of process. So this is just ping and pit, and in Java we should write something like this. So the main thing is how to receive, because in Java, we should write a lot of code to cast, to check the types and check arities and control types and convert types and so on. And you see that in modern Java, this is like more readable and more functionally, but of course we have like nested switches and manual instruction, and in just 3 lines of Erlang we should write much lines in Java, and you see that in Erlang we do fully automatically pattern matching, extract second, first, bind variables. In Java, we should check types, check arities, do casting, checking values, and this is just a small example of ping pong says us that code size is 5-10 times larger and a lot of possible runtime errors. We see in also this way just Java do some Java did some evolution. The Java developers borrow a lot from functional languages. They do pattern pattern matching, for instance, of pattern matching for switch. Do record. They propose records and so on. And we see that code code in Java is improving, but still remains more cumbersome than Erlang, and because of static type system and no built-on pattern matching for Erlang style tuples. So you see that we can see that also they introduced virtual trees, but to interact with Java and using J interface, we do not use this. And you see that we still have problem with pattern matchings with tuples. So this is a good way to show the difference, to show the evolution of languages like Java. They started to do more looks like Erlang in some ways, but still we have some troubles, and we see that Erlang code is much understandable and error free, and so the students love this example to understand the power of Erlang. After I'm moving to lightweight process and TCP server, because I think TCP server, this is a good idea to implement in Erlang because as usual, developers create a thread per connection, and of course TCP server is also can be exchanged with programs in different languages, and we see just a comparison with different languages and Erlang again, and you see as a rule, because just before Java Loom project, developers used thread pool and non-blocking I/O, and developers think more about infrastructure, not business logic. You see that in Erlang we just could start one lightweight beam process, and we care about clients and connections. We see they are visible, and we do not think about artificial entities like thread pools and how to organize non-blocking I/O and so on. So easy TCP server using listening and looping on receiving, then if client comes, we get a client socket and do some recursion, and we see that we spawn this in a lightweight Erlang thread, Erlang process, and see that server is just 10 lines of code. And the best way to demonstrate this in a weak hardware, you see this very old computer. This is AMD Geode, about 500 megahertz and half of gigabyte of RAM, and this running anti-X Linux, especially for this hardware. And we spawn a lot of clients to connect with server running on this, and you see that just sending messages, sending socket through the server socket, and each client connection also runs separate lightweight process. So this is like aha moment. During the demo, we increase number of connections, watch netstat, that connections are still alive, and we receive thousands of established connections, and the server remains responsible, and the SSH session is also works. So I think bring this old hardware is a good point to demonstrate the power of Erlang, because if we could do this in this hardware, what we could do in a powerful hardware, students, I think, understand this moment. So, of course, in Java, they are not sitting just on a chair. They introduce things like virtual trees and lightweight, just borrowing, I think, some concepts from Erlang, but we see a lot of differences. The Java threads share memory, and no built-in actor model, no supervisor, no loaded crash, and so still with having virtual threads, Erlang offer a more comprehensive solution for reliable distributed systems. And now I'm moving to a good example of POET consensus protocol in Erlang, because I think in Erlang we could easily model protocols, and we should share this experience to students. We see that in traditional imperative language, we should do a lot of with thread management logs and share data, so hide the essence of the protocol. And in Erlang, we could focus on protocol logic, not low-level concurrency. And we see that there is a proof of elapsed time protocol exists, introduced by Hyperledger SAO2 blockchain, and they use Intel HGX hardware model for secure random delays. So a node just request around from network, and it sleeps for some time, and the first node that awakes, that generate a new block in blockchain. And I have some paper on this, and this is about verification, but I wrote the protocol firstly in Erlang, and we have some processes. We have we have just SGX similarity, just generate random values, nothing about reality, but this is a model. So the model is fully available on my GitHub, and this is a good demo to just show students how to model real protocol with real real nodes that generate that do some consensus and generate blocks. And we see that this is about 100 lines of Erlang code, and this is like more understandable than any model of protocol in imperative language. So I would also finish with verification of actor systems because I love model checking, and we see that model checking can explore all possible states of a distributed system model. And from the beginning of my research, I use spin model checking, and they have a Promela language. Promela means protocol meta language, and it's quite similar, but Erlang, but they use channels instead of bits, and this is like not a functional language, but language of interoperations, and we can compare two languages. Erlang is based on actor model or p-calculus. There are some papers, and Promela is CSP. This is sequence processors processes by Huar, and in my teaching experience, we just introduced some examples like ping pong in Promela, and we verify some properties, and students introduce some LTL formulas, insert some variables, and they convert their models previously written in Erlang to Promela. And then, for example, in the paper, you see this verification of airport model, and a lot of processes are interoperating, and using verification, we can prove some properties. But the initial model was written in Erlang, then students convert this to Promela because they share the same actor knowledge, and they use AI probably, but AI, I think, is not good for Promela, and so they still requires manual work. So it's a good way to write some real hand code, and so verification is a logical continuation of actor-based thinking, I think. So also we have labs approach. We start from simple processes, distribution, Java integration, then study OTP, hot code swapping, verification, and also for good students, they also port programs in Erlang to Haskell using Cloud Haskell Cloud library. So we have some demo system, bank or communicator, and we evolve them with students through this semester. Okay. Also, I would like to stress some AI challenges. We have competence hollowing because now I see students mostly do not understand some. For example, they cannot answer the question how to send PID to from Erlang, for example, because they know that they should use this operator, but it's like forget what to do exactly. But we see we have before LLMs, I had 70 question syntax test, and the scores were okay. But now we use offline tests, and syntax test, I think now is impractical, and because something like that was there. And but if we continue live coding in incremental development, I think we could do a good a real course in AI era. We still can have a good course on programming language. Okay, more than 100 students finished the course, and a lot of alumni work with side technologies like Kafka, RabbitMQ, Go solutions. And one student said, I understood, thank you. I understand what patch matching is, and now I use it everywhere. And already started to be synonymous with reliable distributed systems. And we do some research on distributed framework, large scale data analysis using Erlang languages. So I finished. Sorry for some time overflow in my presentation. Okay. Yes.
Thank you very much.
Thank you.
Thank you, yeah. All right, we've got a 30-minute break, and then we will be back with James Harton. He will be speaking. So that will be at 4 local time. Thank you.
Okay, thank you.
Our next speaker is James Harton, a principal engineer at Alembic and a core member of the ASH team. James has been building production systems with Elixir for more than a decade and is the author of Reactor, ASH Authentication, and numerous other libraries in the Elixir ecosystem. James will take us inside one of those projects with Reactor under the hood, building a graph-based Saga orchestrator in Elixir. Please welcome James Harton.
Hi, everyone. Take it you can hear me okay?
Yes.
Yes, excellent. Okay. So, hi. I'm James, and now you know everything about me. I'm going to tell you a story about the best loop I ever wrote. That loop sits at the heart of Reactor, a Saga orchestrator for Elixir. To understand why I care so much about a fairly unassuming with expression, we're going to start with the workflow model and then dive into the executor where concurrency, nested workflows, failure recovery, and retry delays all meet. We'll follow one small workflow from its DSL into Reactor's executor. Along the way, we'll hit two places where a nice, easy design met the real world and didn't agree. So let's go. Now, I have a whole slide to read, but actually, you've just heard all about me. The only thing to add is that I live in a small town outside of Wellington in New Zealand. It's 8 a.m. in the morning, and that's why I have coffee. And I've recently acquired my third dog, but that's still not enough dogs. Okay. Reactor is a dynamic concurrent dependency solving Saga orchestrator. That's a dense sentence, so let's unpack it. A Saga breaks large operation into steps. Successful steps can undo their work if a later step fails, while a failed step can compensate for its own failure, hopefully. That gives us transaction-like semantics across boundaries where a database transaction couldn't help. HTTP APIs, queues, files, or even several different data stores. Dynamic means the workflow can change while it runs. Concurrent means independent steps can run together at the same time. Dependency resolving means you describe what each step needs rather than manually prescribing the execution order. Reactor turns those descriptions into a plan and works out what it can run next. Reactor grew out of the work in the Ash ecosystem, but it's a standalone library, and you don't need to use Ash to use Reactor. So the central model of Reactor is a directed graph. Each named step becomes a vertex, and when an argument refers to another step's result, that reference becomes an edge. Reactor builds the graph and checks it for cycles. A cycle would mean that at some step eventually depends on itself, so there's no valid starting point. Rejecting that during planning is much nicer than letting the reactor spin forever. The useful part is that the graph does two jobs. It records ordering constraints and it exposes concurrency. Any vertices whose dependencies have been satisfied, i.e. have no inbound edges, are ready together. We get scheduling information without maintaining a second parallel description of the workflow. So here's a really small and contrived reactor. It takes an email address and a password, and the first two steps each depend only on input, so neither depends on the other. The final step consumes both results, and the reactor returns the final result. The DSL is describing the problem at one level of abstraction. These are the inputs, these are the steps, these are the dependencies. The step modules contain the actual work. You can build the same structure programmatically with Reactor's Builder API, but I'm using the DSL here because it's easy to read on a slide. Also, the declarations can appear in any order. The graph, rather than their position in this file, determines the execution order. So this is the execution view of that code. Validate email and hash password are both ready immediately, so Reactor starts them together. Create user is blocked until both results arrive. Once it succeeds, its result is used as the return value. There's no separate list saying first do these two, then do this one. The shape falls out of the dependencies in the graph. That matters much more in a real workflow where there may be dozens of steps, branches introduced at runtime, and several independent paths moving at once. The DSL order is arbitrary. The graph, rather than the position in the file, determines execution order. I still do recommend writing it in an order that helps the next human. Reactor does not care about your future self, but your future self at 2 a.m. might. That's when everything goes well, but let's look at what happens when something goes wrong. On the failure path, Reactor works at 2 levels. First level is compensation, and that handles a step's failed attempt. It receives the failure and can ask the reactor to retry the step, continue with a replacement value, or return an error. Undo operates at the wider Saga level. It runs for work that previously succeeded when the Saga can no longer complete. A create user step might compensate for its own timeout by requesting a retry, but undo a successful request by deleting the user after some later step fails. So compensation decides what happens after this attempt fails. Undo reverses earlier successes after compensation has failed. So here's how that might look in code. This is, again, the contrived create user module. The step block on this, on the earlier slide referred to it, but this is where the work is done. Steps implement the reactor step behavior. So run does the work while compensate and undo handle the 2 levels we just described. The compensation callback retries only transport timeouts in this case. Other failures are returned as errors, so Reactor can begin the wider failure handling rather than repeatedly trying something we do not understand. Retries are bounded. Steps can declare a maximum, and once it's reached, Reactor stops asking. Undo has its own contract. It must return OK, retry, a retry tuple, or an error tuple. Returning Rec's successful response directly wouldn't be valid in this case. Reactor also limits undo retries independently to 5 attempts, so this callback cannot retry forever. Now we're going to go under the DSL, where the executor has to run all that while the ground is moving. Concurrency is finite. Steps can add more steps. Tasks finish out of order. Failures trigger compensation, retries, or undo. A compose step can run another reactor inside the parent, and the whole run could time out. You could model that as a large state machine, but Reactor instead uses a small loop of stages with consistent return shapes. So this is the basic description of the scheduling loop. Each stage asks exactly one question, and anything other than continue returns immediately to the dispatcher. 4 outcomes control execution, and 2 more are terminal. Continue, recurse, halt, and undo tell the loop what to do next. The success and error tuples are results that leave the loop entirely. The one outcome worth remembering is recurse. It starts the loop again and spends an iteration from the run's budget. Stage 7 is the odd one out. Try the nested escape hatch is not a scheduling strategy anyone would design in from first principles. It exists because of a specific problem, and to explain that problem, I need to show you how Reactor counts concurrency. Reactor controls asynchronous work with shared concurrency pools. Unless told otherwise, max concurrency is the number of online schedulers. If asynchronous execution is disabled, that limit is 0. A run can receive an explicit concurrency key. Runs with the same key draw from the same pool, which prevents each nested or related run from independently trying to saturate all the cores. Reactor's compose step passes its parent key into the child reactor, so the entire tree of composed workflows shares one finite counter. That sharing is deliberate. Without it, a workflow that composes 10 children would happily start 10 machines worth of tasks. And let's look at how the pool works. It's really simple. Allocating a pool creates a reference and inserts one ETS record. The pool reference, configured limit, the currently available slots, and the owner PID. Available capacity starts at the full limit, obviously. The shared counter lives in ETS, where callers update directly and atomically. The tracker gen server stays responsible for table ownership and cleanup. If a pool owner exits, the monitor lets the tracker remove the record rather than leaking rows. So one integer shared by an entire tree of composed workflows, decremented by whoever gets there first. That's a good design, but it has one surprising consequence. Say the shared pool has 6 slots, and the parent reactor is already using 5 of them. A compose step takes the 6th and starts a child reactor using the same pool. The child has ready asynchronous work, but it cannot acquire a slot. The compose step cannot finish until the child finishes. The parent cannot release that last slot until the compose step finishes. Everyone is doing the right thing, but no one can make progress. So, and the size of the pool doesn't matter. This happens whenever the outer work consumes all shared capacity before nested work can get started. Increasing the pool only makes the same bug arrive under a larger workload, which is a traditional way of postponing an unpleasant afternoon. This is the first of my 2 awkward edges, and I would love to tell you I saw it coming. What actually happened is that a user opened an issue, and I could not get to the bottom of it until my friend and collaborator, Zach Daniel, said he'd seen something like it in Ash's original workflow engine. Here's the fix. This is the stage 7 we talked about, and it's the 3rd scheduling attempt. First, the executor tries to start ready asynchronous steps using pool capacity. If it cannot progress, it tries a step that was explicitly declared synchronous, and only then may it run any ready step in the current process. And even that has an exact guard. The process dictionary must already contain the same concurrency key. That proves that the child reactor is executing inside a step which has already acquired capacity from this pool. So the reactor is not casually bypassing the concurrency limit, it's using the slot occupied by the enclosing compose step, which is blocked waiting anyway. Without the matching key, an ordinary top-level run cannot take this escape hatch at all. Deadlock resolved. Let's climb back up the loop. So 8 stages might be easier to think about as 3 movements. First, guard, plan, and collect. Check the timeout, take in dynamic changes, gather completed tasks, and ask the graph what's ready next. Schedule tries asynchronous work first, declares synchronous work, then the escape hatch we just built. And then lastly, settle, check for completion, i.e. there's no more steps to run, and start all over if needed. There's no scheduling policy written down anywhere else. The order of these stages is it. The escape hatch comes last because it comes after everything that respects capacity, and completion is checked only once every other source of work is exhausted. And here it is. Every stage in one screen. Elixir's with expression gives us a straight pipeline. Each stage must return continue for evaluation to reach the next one. And any other tuple jumps immediately to the matching else branch. Recurse starts again with updated state, decrementing the maximum iteration allowance. Halt, undo, success, and error leave through their own branches, which I've omitted so the slide stays readable. This is the scheduling spine rather than the whole executor. Lifecycle hooks and cleanup sit around it. Now, I told you at the start that this was the best loop I ever wrote, but before you take my word for it, there's something I've left out. This isn't quite the final loop. There's one more stage and one more outcome, and they're here because a year ago I broke it. So last year in September, I had the joy of going to Goatmeyer in Sweden. And I came home in October with the usual post-conference combination of a head full of ideas and completely unjustified confidence that all of them would be easy. One of those ideas was retry backoff. Reactor could already retry a failed step, but there was no delay. The step simply became ready again. I wanted compensation to be able to say, try that again, but give it a moment. And I wanted it without building a second scheduler beside the graph. I had the loop, I had the graph, and I found a pleasantly small way to join them together, and it worked. I declared victory, shipped it, and forgot about it completely. Retry delays are represented inside the same graph as the workflow. A back-off vertex sits between a failed step and its next attempt. Until that vertex expires, the dependency prevents the step from becoming ready. The executor finds expired back-offs and deletes them as part of the loop. Removing the vertices also removes the dependency edges, so the ordinary ready step calculation can discover the retry. The graph still carries the state. There's no second map of delayed step names to reconcile it with. That was the whole initial implementation, and a vertex when a retry needs to wait. Add a vertex when a retry needs to wait, and then add one stage to the loop which removes expired vertices. No timers, no second scheduler, no special retry state. I was extremely pleased with myself and crowed about it at CodeBeam last year. Months later, someone opened an issue. There was one small problem. I had modeled the step when the step could run again, but I had not told the executor how to wait. With no runnable work and an unexpired backoff, the loop immediately started over. Every pass called subtract iteration, so a run with a finite iteration budget could burn through it and halt before the backoff ever expired. But with an infinite iteration budget, it eventually retried, but spent the whole delay sprinting through the loop. So depending on the run options, the backoff either stopped the reactor before the retry or turned it into a tiny space heater. The graph model was doing exactly what I asked, keeping the step blocked until its dependency expired. The mistake was in the loop around it. I had added a stage to remove expired backoffs without considering what happened when none of them had expired. So here's the second escape hatch, and with it, the final version of the loop. I didn't write this. Mario Caput opened the issue, and 6 hours later sent the fix from Poland while I was asleep. The fix added two things. First, a 10th stage, which runs only after every immediate source of progress and completion check have said continue. There are no ready steps and no running tasks. It finds the earliest backoff and sleeps. The sleep is capped at a second and by reactor's remaining timeout, so the executor still wakes up periodically to check the world. Second, waiting returns a new control outcome, spin. Like recurse, spin starts the loop again, but unlike recurse, it doesn't spend an iteration. It's the whole bug fix. Sleeping stops the CPU burn and spin stops the iteration budget draining while the clock advances. The change is one stage and one outcome added at the one place in the loop where there is nothing to do right now is finally known to be true. That is why the count went from 8 to 10 and from 4 outcomes to 5, and that's the loop complete. So every question in the system has one place it gets answered. What depends on what and when a retry may run lives in the graph. How a failure is handled, compensate and undo. How much may run at once, the concurrency tracker. And what happens next is the stage ordering. We looked at 2 escape hatches, and I want to be clear that they are both the same lesson told twice. I didn't see either of them coming. Both of them arrived as bug reports from outside users. One I could not diagnose until Zach recognized the shape of it, and the other I'd shipped and forgotten about. In both cases, the hard part was understanding the problem, not repairing it. The repair was one stage, one guard, one outcome, and the second one I didn't even write. Somebody who does not live inside this code base like I do put it in exactly the right place without touching the graph model, compensation, or the tracker. That's the strongest thing I can say for the design. Not that it made me clever, but it made the fix obvious to someone I've never even met. Simple code is not automatically correct. Good design does not pretend the problem is simple either. It gives you every piece of complexity. It gives every piece of complexity one place to live, so that the hard thing ends up looking obvious. And that's why it's my favorite loop. not because it's easy to write, but because it's easy to read. I'd like to thank Alembic, who give me amazing time and space to work on things like Reactor and share it with you. Alembic is a software consultancy specializing in Elixir and Ash. We're a globally distributed team headquartered in Sydney. If you have a project in mind that we can help with, please don't hesitate to get in touch. And thanks for coming on the tour. Reactor is on Hex and the project is open source. The documentation is on HexDocs and the source is on GitHub in the Ash project organization. The source is worth reading if the loop interests you. The stages are small enough to inspect one at a time, and the tests capture the less obvious cases around shared concurrency and nested runs. I'm happy to take questions about the executor, the Saga model, using Reactor without Ash, or the mistakes that did not fit into this talk. If there's something I cannot answer live, come and find me online afterwards and I'll dig into it properly. And thanks for letting me talk to you about loops, and I hope the video didn't buffer too badly as it traveled around the globe. And that is the end, 10 minutes faster than practiced.
All right, we don't have any online questions.
Doesn't
How
look like
about
it.
here? What?
You're right. I'm looking at the channel. It's empty.
Okay. Anybody? Yeah. We need the mic held back there.
All right. So, thanks. This was a fun talk. I guess often good design is easier to recognize in hindsight than to plan for. And I was wondering if either along the way or as a consequence of this, if you learned things that help figure out how to anticipate or plan for or steer towards good designs like this.
Well, I can tell you that the early versions of Reactor, or not early versions because it was unreleased, the early, spikes were not good. And they were state machines and horrible things like that I mentioned on the way. And I was listening to, I don't know which Elixir podcast, because unfortunately they all kind of blend together in my ADHD brain, but there was one where someone said, I write with statements where I match on the error cases. And it sort of unlocked a thought technology for me where I was like, oh, of course. It doesn't just have to be okay, arrow, okay, arrow, which is what you see most.
Yeah.
And then all of a sudden, the beginnings of the design started to appear in my brain. So I'm grateful to whoever that podcast person was, because I think they are responsible for most of this.
Okay. Cool. Thanks.
So
no questions, Jonathan.
I've got a question, but maybe a little tangential.
Yeah.
So my undergraduate senior students contribute to the Ash framework.
Yes.
And Reactor is one of the things they contribute to.
Yeah.
And once they catch the vision, once they can, it's one of their favorite libraries to work in.
Yeah.
The trick is, how do I help them more easily understand? I mean, they've learned about graphs, right? They've learned about directed graphs in previous classes, and they probably don't understand them just because they've been in a class.
Yeah.
So how can I help them link the theoretical of the graph that they've learned and what you're doing in Reactor so that they can contribute more readily?
Yeah, it's interesting because I didn't initially understand that what I was doing was a graph problem. I was busy thinking about the declarative workflow. But one of the nice things is that Reactor does have a graph, and it's part of the Reactor struct. And we have some mixed tasks to actually visualize it into like a mermaid chart. So it can be quite helpful to show the workflow, say, look, there's step X, step Y, step Z, arguments between them. Here's the graph. Here's what the graph actually looks like when generated, with the links between them, and that might help. I don't know if it will, but that's the first thing that comes to mind.
Okay, all right, thank you. Thank you. Anything else? All right, thank you very much.
Yeah, thank you.
So I just plug in over here. So I was well along the path for doing the Rust conversion. And I was fighting with the operating system because it kept moving my allocated memory on me when I was trying to get it to use the JIT libraries. And but I was real close. I was real close. It was exciting. And last Christmas, on the 24th, I was sitting pondering this problem and how I was going to resolve it. And it came to me that I was solving the wrong problem. Because no matter what I did with this Rust conversion, I was eventually going to have to jump out to C libraries anyway, and now everybody's got the same argument. The JIT library was written in C. A whole bunch of these other sub-libraries were written in C. So I came to the realization I was solving the wrong problem. And what I needed was to write this in a language that was different. And it had to be different in many ways. And it had to more closely represent the chips that we have. The Erlang Beam is an amazing piece of software, a work of genius. It is a work of genius. And it anticipated what our chips look like today. The way it works is much like our modern chips. Our modern chips aren't single core. It was written when there was just the CPU in one core. Okay? It anticipated multi-core. It anticipated all kinds of things. And the problem is, as I was thinking about this, the problem is we take all of that incredibly amazing, cool stuff, and through the C compiler, we turn it into a PDP-11 from 1969, and then we rely on the compiler's optimization algorithms to spread it back out to what it was essentially originally. So we've got this bottleneck that's unneedful. There is a much more direct mapping of the Beam languages to the modern chips that could be leveraged. And as I was thinking about this, I was like, okay, I need to pick a language that will let me do this. Okay, well, I know I can't use C or C++ and not Rust. And I know I can't use this. And it came down to the point where there was not a language that would let me do it. There wasn't. Okay, and I went, well, okay. I guess I'm going to have to create my own language. Well, I know how to do a new language using LLVM. And then I went, oh, wait a second. LLVM is going to give me the same bottleneck. So I was like, all right. I guess I'm going to have to just go for it and create the compiler from scratch. Okay. So how is Silica different then? Side effects in functional programming languages are a big deal. They are a big deal. And they're kind of clipped onto the side in a lot of these languages. And actors, huge. Memory safety, huge. Okay. I wanted all of that to be in one thing rather than hooking stuff on the outside, putting if statements in to make sure somebody's not doing something bad, all those kinds of things. And so this was one of the reasons that Silica ended up taking the shape that it does. Okay? And again, I'm not just doing this for kicks and giggles. Right? Anybody that thinks creating anything beyond a toy language, you're going to do it for kicks and giggles does not understand. But I wanted to kill bugs in software as fast as they can be killed long before the software runs. Okay. So Silica is a systems language. I want to match the chipset as close as I possibly can. Okay? So and to make that happen, that means I'm working in a system language, a language designed to create operating systems, virtual machines, drivers, that sort of a thing. Yet it can be used to create applications. Okay, you'll be limited by the operating system that you run it on. You won't have full access to everything the chip can do because of the choices made by the operating system writers. But when you drop out onto raw hardware, you can have that direct access. So Arch64 is the initial target simply because I have Arch64 machines. And our next target is, as you can see, ESP32S3, because this is a board that we give out at BYU Idaho to every incoming freshman, and they do all of their initial programming classes on it. Okay? So they write code to run everything on this board, and it has extensions, you know, all the good stuff that cool boards have. And we want Silica to run on that as our first port. So you can see that. So what in the world does a language look like when these things really are first class, not tucked in on the side? Right? That has been the funnest part of this. Okay? I'm not going to show you yet. So I've been working in the Beam for a long time. I was telling you about that, the Rust conversion. So I wanted to make sure I took everything that I had learned from working in the Beam and on the Beam itself in that conversion and integrated into this new language. I wanted things that were not first class to be first class, not just to make them first class for whatever reason, but because anything that is a chip behavior needs to be first class. So if I have more cores, if I have more than one core, I need, as the programmer, to be able to decide which core this actor runs on. I need to be able to move actors between cores. I need to be able to do all of these kinds of things. I need to be able to decide how memory is used, okay? I need to decide so much, but doing it in languages like C is so dangerous. And surely there's a way I can do it using everything that I've learned from this genius thing called the Beam to make it easier and better. Okay. All right. So the first thing I did was I got rid of the heap. And everybody's going to, bunch of people are going to go, what are you going to do if you get rid of the heap? Well, it makes life easier in a lot of ways when you get rid of the heap. Everything's in the stack. The stack is flexible. You're going to have an right? An out of memory, there we go. An out of memory error on your machine. You won't have a stack overflow. Okay. Each actor has its very own stack. And there's no GC at all. It's not needed. And this one, again, is big for me. If I try to do something wrong in memory, just at all, I need to have a compiler error for that. I don't want to have some memory error cause something to crash. I want a compiler error. So these are all design things that were part of the initial design for the language. Another one, and this could be a little disturbing for some people. If I bind a value to a variable, and then I never use the variable, it shouldn't just say, well, okay, I'll optimize that out. No, it should be a compiler error. Because that way, there's no question that it was done accidentally and somebody thinks something else is going to be happening. Okay? The same thing that we were talking about before. I call the same function twice within the same scope with exactly the same parameters. That's probably not what the programmer intended, and then we bind them to two separate variables. That should be a compiler error. Okay. I've got recursion, but no variation going on. Okay, that should be a compiler error. Okay. Guards that don't do anything, that should be a compiler error. Okay. So all of these things. But one of the things about the Silica's design is that this is to be true. Intent of the code must be visible. Okay, we're not going to rely on some optimizer to behind the scenes magically make it better for us, because then we don't know what our code does. All right. Is it? There we go. So the FFI library, and there is one. I call it Fifi instead of just FFI. Because as soon as I said FFI in my head, Fifi got stuck in there. And I saw this, essentially this picture in my head. And you can think of Fifi as that nice little fluffy poodle. And you go to pick it up and you pet it, and then it just goes bonkers and starts biting you. Because FFI looks like a really nice way to solve your problem until it doesn't. And now you've got crashes out there in some C code or something. So in Silica, all FFI calls have to be inside of an actor. And the actor traps as much of those FFI errors, the memory errors or whatever, the crashes, it does its very best to keep those inside of its stack and to catch them and then restart. Okay? Every FFI call has to come from within a module that has dangerous underscore in its name. And anything that uses that module has to have dangerous underscore in its name. Because one of the problems I've seen with languages that try to do something similar is danger hiding. And so when something goes wrong, you have to go find where that dangerous code was executing. Whereas this cascading all the way up through the users tree gives you a graph that you can easily follow down. You can separate your dangerous code easily from your code that's not dangerous. So again, not hiding anything. We're not trying to hide anything. Make it easy, but don't hide stuff. And also, you can see there that if I'm receiving data from someplace else, it's going to have a taint. We're going to know we need to be careful about it. And this makes our security audits a lot easier to pull off. So this again will make some people upset. Part of the design for Silica is that, I'm quickly running out of time, is that it is designed to be LLM friendly and human readable. All of our modern languages are designed to be read and understood by human beings. And that's one of the reasons why LLMs struggle with them. So Silica is an attempted design, an attempted implementation that makes it easier for LLMs to reason, if you want to use that word, I don't like to use it, reason about what should be done and reason about the existing code set. When you get a compiler error, it doesn't say unknown error, okay? You've probably all seen that in some way. No. It gives you a human readable section, it gives you an LLM friendly section, and both of them point you back to a specific numbered spot in the specification that was violated. Okay, so you can actually, the LLM can then come back and say, hey, well, this is what it probably should have looked like, instead of just, I don't know what it means. Okay, and again, it's not about vibe coding. I am not into vibe coding. That is, in my opinion, you're gonna die young if you're doing that. But just being maintainable. Okay. All right. So we're getting close to the end. So this is, again, why this new language? Because I was trying to rework the Beam. And I have moved a lot of the things the Beam does down into the Silica language to be really first-class citizens. So supervisors are down there, first-class citizens. Actors are down there, first-class citizens. They're not a library, okay? A lot of the things that you're used to working with are first class. And so the idea is, when I get this to be fully when I get Silica to be fully self-hosted, and I'm like this close, then I start working on Project Bees. And Project Bees, that stands for Beam Execution Surface. And it's a shim that implements the things that are currently in the Beam that are not down as first-class citizens in the language. The concept being not to replace the Beam languages, but to allow Silica to be an IR, an intermediary representation language, so that Elixir, Erlang, Gleam, all of these wonderful Beam languages can run at chip speeds instead of on a VM with JIT and garbage collection. Okay. And then this is way out in space. Okay, this is way out in space. So the question is, well, is this slideware or what? Well, Project Bees and Organism, yes, they're slideware. Okay, but Silica is not. On July 24th, or December 24th of last year, 2025, I started thinking about the design. At the end of February, I had a bootstrap compiler done and started working on the first version of the Silica compiler written in Silica. During that process, and in writing all of the continuous integration tests to drive that development, I realized I needed to do a dialect shift. Not a dramatic thing, but a dialect shift within Silica. And so I had the new compiler, the Silica compiler. I'm not saying this well. I had the Silica compiler that was compiled by Rust do all of the continuous integration tests in the new dialect. And now I'm turning it on itself. The Silica compiler is now running against those same continuous integration tests. There are currently 2,000 of them. And there are two groupings that, of all of the groupings, there's only two that do not yet pass. One is the Fifi stuff. It's got one compiler bug in it. And then the first-class data structures, which currently consist of just ordered binary search tree and ordered set. And later will include graph, directed graph, and a bunch of other things that will be first-class citizens in the language, because it doesn't make any sense not to. So when I said I'm that close, as soon as, hopefully by the end of next week, both of those are passing their continuous integration, and I turn that version of the compiler on its own source code because it needs the standard data structures, and finish it out for its first proto-release. At that point, we'll start our next port. So I am thrilled with how far I've been able to get in, 9 months? It has been astounding, and I feel greatly blessed to have been a part of doing this. Questions that you have for me? Yes?
First question, I assume you used LLMs for the process. I wonder how. And the second question, before the talk, you mentioned something about operating systems. So does this work on any operating system, or it needs to work on bare hardware, or what?
Okay. So yes, I did use LLMs. There's no way that I could have gotten where I am if I had not. But again, it is not vibe coded. An LLM can type a lot faster than I can. And yes, I did go through first with a highly detailed specification document. And that's available in the GitHub repo as well. And so I was leveraging that, and then gradually over time, because I was using Cursor and Codex, and both of them are aware of the code base that it is working on. And so gradually over time, they got better and better, not because the model learned anything, but because I had more and more good code that they could work against. The current target is Arch64 and Mac OS, because that's the machines I've got. One of the next low fruit is Debian on the same Arch64, so Raspberry Pi kind of stuff. And then raw hardware off of this. Essentially, all you really need to do is modify the emitter to create the assembly for whatever chip you're running on and whatever operating system makes it available. And you've got a port.
Do you need to bypass the operating system, or can you work on an existing operating system?
You can do it on an existing operating system. If you write for that operating system, there are some things in the Silica design that you can't do because the operating systems restrict you on what you can do with the hardware. So, more questions? Over here.
Cool talk. Very interesting project. I think I have two questions. So one is you have picked quite a menagerie of different ideas to fuse together into this language design. And I'm a fan of fusing complementary ideas together, but I'm curious how you picked these ones and how you're managing that integration. Maybe I'll ask the second one after.
Okay. So I am a language geek. I love computer languages. I love human spoken written languages. And I've written code in a lot of different languages. And on a lot of different virtual machines. And a lot of direct OS code as well. And I thought of all the things that I hated, all the things that the shackles that were put on me, and said, why? And that was one of my initial starting points. That's always been one of my major questions in life, is why? You know, a manager says, well, this is the direction we need to go. The first word that pops into my mind is why. Could you please explain that to me? It didn't make me very popular when I was in industry. So that was, there were things I loved, and there were things I knew that the chips could do that I was not being allowed to do, and I wanted to make sure that all of those things were made available to me in silica. And how do I manage it? I don't know.
Just fits
It makes
together in your
sense
head
in
that
my
way.
head.
That's how it goes sometimes. Cool. And then, you know, earlier you and I were talking about like device drivers in this kind of framework, and you know, hardware is bizarre and flakier than most of us would like to admit.
Yes.
And so I'm curious if this, you know, about sort of that and the FFI, if those are distinct, or if the FFI is trying to deal with some of those issues, or how you're looking in that space.
So I really didn't want Fifi in there at all. But in order to do this first port, given the time frame that I had, I didn't want to have to rewrite the HTTP stack because I couldn't fit it into the time frame.
Sure. Yeah, those are big.
And other things as well, right? You know, for poking things, that sort of stuff. And so I was like, okay, but because it's in here, I'm going to make sure everybody knows that it's unsafe, and anything that uses it is unsafe, and so that's why that's in there. The idea is that we, over time, replace that code with the poking code written in silica and all that kind of goodie.
Okay, cool. So it's kind of like a intermittent developmental stage.
Yeah, yeah.
Okay, cool.
Yeah, this is not version 1.0 that will be available hopefully in the next month.
Nice.
I want to jump on the LLM friendly question. What does it mean for the language to be LLM friendly? And
Okay.
it seems like the big problem now is tokens. How much
Yeah.
token cost is it to get the next response? So I'm thinking about what you do for error messages, how you point to a part of the specification. It might be useful to ask LLM to come up with an encoding scheme. Take this specification and condense it down to the minimum number of tokens. And then same thing for the error message. You've got a draft of the error message, condense that into a small number of tokens.
Yeah.
Because I'm not sure myself what would be a good way to reduce token use, but
So-
maybe the LLM knows best.
So I've actually played with that, and I've tried many things. Most of them are not lossless. And that's the issue we run into. These things are designed for understanding, put that in giant air quotes, are not designed to work with anything except human-style language. And when you start to do other things with it, it can get really strange. One thing that I have found is that the more structured the data is, the fewer tokens it uses, and the easier it is for it to work with the data. The idea that it's great at just, you know, unstructured data, it's not as great at it as structured data. And so I can show you, I think I've got one of these that's...
Yeah, I'm curious what counts as structured data. JSON as expression?
Well, there's a version of JSON that expresses a graph, and I've used that. The problem is that uses a large number of tokens. It reacts really well to the data being structured that way, but it uses a lot of tokens. All right, I'll pick this one. Oh, let's see, we want to go over here to the side. No, we don't. We want, go away. That's the wrong thing. Okay. We'll come down here to the trials to speak to your, where'd it go? To speak to your question about what the errors look like. They look like this, starting with the red X there. So the first part is the human readable part, and then at the bottom you have the part that is easily consumed by the LLM. And again, it refers back to the section in the specification so that the LLM can then go, oh, okay, now I understand what this means. More questions? The other part, you have a question?
Yeah, do you have any plans to mechanize or verify any parts of the compiler?
So if you dive into the specification, so first of all, the continuous integration stuff is about the compiler. So I'm doing testing to partially get there. Let me close that up. There's a few of those. If you go down to the compiler specification, and we can get there through the README somewhere. Shoot. You will find that formal verification is included in the design specification for the language. I haven't added it yet. Okay. And then also, there's some other work in there too that makes it easier to make sure the messages that are being sent back and forth within the compiler between actors is also correct. And that makes the formal verification much easier too. Did that answer your question? So I can put in the formal verification in the compiler because it's not quite there yet. We're not at version 1.0. But more questions? Okay. Well, thank you very much. This has been so much fun to do, and that sounds awfully weird when you think about creating a new language. It's just been so much fun. Thank you very much. All right. So here we are at the end of the day, the end of the conference. And again, I want to thank everyone who has participated, all of the people who have presented, all of the people who have come, all of the people who have come online. And I would once again like to thank our sponsors. Without them, this would not have been possible. If you do research in this area, please, please, please strongly consider becoming a paying member of the Erlang Ecosystem Foundation, the ERLEF. ERLEF.org, easy to find. It's not a lot of money. Okay. They do very important things. So, also Ericsson, thank them, and Dashbit. They recognize, Ericsson, of course, is the original producer and still contributes humongously to the Beam. And Dashbit, heavy user. So they recognize how important what we do is as a community, and so they want to support us. So thank you very much for coming. Thank you for participating. It has been a joy for me.